Alo, các thầy trong hội trường mà mình có tham gia trong cái trực tiếp online á, thì các thầy lưu ý giúp giùm em á, là mình không có mở mic chung, tức là trong mỗi lần mình chỉ một người duy nhất trong hội trường của mình mở mic thôi. Chứ nếu không là mình sẽ bị hú cái phần âm thanh lên trên cái hội nghị online của mình. Xin cảm ơn.
Hello. Hello. Good morning. Hello. Good morning, ladies and gentlemen. Welcome to OU. Hello. 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 Hola. Good morning, ladies and gentlemen. Welcome to the International Conference Structural Health Monitoring and Engineering Structures. Ladies and gentlemen, today we would like to invite President of Ho Chi Minh City Open University to start the program. Start. It's trial. It's not really official opening. Okay, rồi. Đi chưa đúng không? Since everyone is here, we should start the program. Good morning, distinguished guests, scholars, researchers, and the faculty and the students from all over the world coming this conference, and the people who could not come to Vietnam. We would like welcome you to attend it online. Because of the disease, we are very pretty. We are very sorry that you could not come to Ho Chi Minh City to attend the conference. To begin the program, we are pleased to have the president of the Ho Chi Minh City Open University, Professor Nguyễn Minh Hà, to deliver the opening remark, please.
Dear distinguished guests, ladies and gentlemen, good morning. On behalf of Ho Chi Minh City Open University, I welcome you and would like to thank you for attending the first international conference on structural health monitoring and engineering structure. The conference should be organized directly at Ho Chi Minh City Open University, exactly in the civil engineering department. But unfortunately, due to coronavirus, we must organize it online and make the participants safety. Hope to see you the next time. We are welcome again. Ho Chi Minh City Open University is a public one that is dedicated to promoting the society with active learning by offering the most flexible arrangement to students using the most appropriate and effective methods of education at undergraduate and postgraduate level. At the Applied Research University in Vietnam, Ho Chi Minh City Open University has developed a research agenda that aims to introduce empirical and scientific evidence to give the policy implications for business, economy, biotechnology, engineering, and social science in Vietnam. We are encouraged to organize the international conference in various fields, and this conference is an example. The objective of the conference is to bring together international scientists and engineers in academy and industry in the fields relating to the structural health monitoring and engineering structure. The conference covered industrial engineering applications to about topics including theoretical and analytical methods, number, numerical simulations, and experimental techniques. One of the aims of the conference is to promote cooperation between international scientists and engineers from a large number of disciplines who are involved in research relating to the structural health monitoring and engineering structure. The conference had different topics relating to the medical, mechanical, and civil engineering. I have seen that this conference received more than 100 abstracts, 18 full-length papers from different countries, and the accepted papers are 60. I would like to thank the chairs of conference for spending a lot of time to successful this important conference, as well as scientific committees for the health, without forgetting the Dr. Lê Thanh Cường, Dr. Samir Katia, and Professor Nguyễn Trọng Phước for more contribution. I would like to thank the keynote speaker for contributions as well as presenters, delegates, and sponsors. Finally, I would like to thank you for your participations and to encourage you to use the network of learning opportunity for this conference presents. I wish you all the best. Stay safe and well. Thank you.
Thank you for your wonderful remark. Now, the conference could not success if without one of the donor here. We have big sponsor, director of the Thành Việt Construction Company, Mr. Nguyễn Quốc Học. Please come to the stage. Thành Việt Construction Company is one of the big company in the construction market. They build a lot of building from industry to office to the apartment, and the companies contribute 25 million to this conference. And the Ho Chi Minh City Open University also have a flower as a gift to the company to thank you for your contribution today. And we also have a certificate to thank you for your present and your financial contribution to our conference. Thank you very much. And the conference, the people behind all the program here, we prepare for the whole years, come from Dr. Lê Thanh Cường, Professor Nguyễn Trọng Phước, and Dr. Sami Kathir. He's online watching us today. I would like to invite both of you. We want to thank you for your time, your effort to organize the whole program to make it happen today. Dr. Sami is not here today, but we...
I'm here. Yeah.
Hi.
Yes,
we
I'm here.
really appreciate your
Okay, thank you.
Your contribution to...
Okay, thank you.
Okay, thank you very much.
Okay, thank you.
And now Dr. Kung will introduce the conference program to the audience today. Please, Mr. Kung.
Yes, I want to hello. Yes, I want to thank you, Professor Nguyễn Minh Hà, for your present. Yes, I'm very proud to be the head of organizations committee of structural health monitoring and engineering structures conference. I had a chance to work with many researchers around the world. After so many efforts, I am very proud that the proceeding of SHM and ES 2020 belong to the lecture notes in civil engineering that will be published by Springer and Index in Succubus and Web of Science. The first keynote speaker is Professor Fu Ku Chang. He is the professor in the Department of Aeronautics and Astronautics at Stanford University. He also is the editor-in-chief of the International Journal of Structural Health Monitoring with the impact factor 4.93. He also the founding chair of the International Aerospace Industry Steering Committee for Structural Health Monitoring. The second keynote speaker is Professor Venkata Rao. He is professor in the Department of Mechanical Engineering, SV, National Institute of Technology, Surat, India. Professor Rao also published more than 350 research papers. I would like to thank Ho Chi Minh City Open University. Also, Professor Nguyễn Mạnh Hà, the president of Ho Chi Minh City Open University, for his guide support. We wish the SHM&ES conference success. There are 5 sections in our conference. Section 1 is the optimization and machine learning for engineering structures. Section 2 is the crack analysis for structural health monitoring. Section 4 is geotechnical and geo-environmental engineering. The final section is experimental and numerical investigation for engineering structures. Now, I would like to introduce Professor Fu Ku Chang from Stanford University, USA, as the first keynote speaker of our conference. And he will present his plan with the title Structural Health Monitoring for Smart City. Yes, Professor Fu Ku Chang, please.
Okay.
Professor, can you hear me?
Can I share? Can you hear me?
Yeah, okay. Yes, we can hear you.
Can I share?
Yes.
Screen share one or the other. So you probably need to turn off your sharing.
Can you let the professor to share his presentation? Kong.
Okay. So I think someone had to turn off the screen.
Kong, can you turn off the sharing? Okay, now okay.
Got it.
Yes, okay, perfect. Yeah.
Okay, let's see. Okay.
Okay, perfect.
Hi, everyone. This is really my pleasure and my honor to join this first conference, I was looking forward to visit you guys, all right? And because when I first saw this announcement, I was so excited because just having a meeting in Vietnam about these topics, and that really indicates the technology enhancement or developments in this South Asia is growing, particularly Vietnam, and really I feel very proud of it. And also I really like to meet you there and see what kind of development you have and what kind of activity there. I think this is definitely an industry and society that require multiple, a group and researchers to work together. All right, I think I'm very happy about it. Although I think, unfortunately, we won't be able to meet each other today, and hopefully we will be able to talk to each other and continuously, and even to meet in the future. All right. Thank you very much. I appreciate your invitation. So what I'd like to talk about today is, since this is a very difficult time, so I want to just give some idea about where I'm coming from, and then talk about the overall the growth of the industries, and particularly in this technology area. So I think this is where Silicon Valley used to be about 30 years ago. All right, where am I? Where's the location of the Stanford, which is in the heart of the Silicon Valley. And this is area that used to be a farm and chickens area. That a lot of chickens used to grow in this area, chicken farm, and a lot of fruits and trees, those kind of stuff. So this is the used to be the the kind of symbol of the Silicon Valley, and also very famous. That's a dish, and you can see the antenna over on the top of that. So this is Stanford, where is it located in the heart of the Silicon Valley, was sponsored and actually founded by a family, Stanford family, actually named after the son of the Stanford. So the name of the Stanford University, the full name is Stanford Junior University, under his name. He died around the age of 16. So this is the campus view. You can see that at the beginning. And then Stanford is famous for the tree, the big tall tree. And across the Bay Area, that is California, of University of California, Berkeley. So this is our rival university. And here is again, it's a beautiful campus. I would like to invite you, have a chance to visit Stanford in the future. Particularly, I think if you are familiar with this community on structural health monitoring, I normally organize this meeting, international workshop on structural health monitoring every other year. And next year, we'll organize this meeting again at Stanford on campus. And you will have an opportunity to visit this place. It's a beautiful place here. And so here is, Stanford actually substantially grow during the Terman years. Terman was our College of this School of Engineering dean, and he brought Hewlett Packard was his students, and to establish this HP. Hewlett Packard is a giant company, and the company down there you can see Verizon, Xerox, Kodak, and all these companies used to be, 1960 are the biggest company in the world, and are growing substantially because of their association with Stanford. And Stanford was also the first university to establish so-called industrial park. So that allowed the company to build their foundations inside the campus. So for instance, if you visit Stanford, you'll recognize that a lot of I live on campus, all right, my house on campus, I would go to this HP headquarters, which is still on campus at Stanford campus. It's only about a mile from my house. So this is this how Stanford would develop. It's on inside the campus. Actually has the industry park, right? A lot of industry actually develop their fundamental technology from the university. And the most important one is Shockley, that the Dr. Shockley invented this semiconductor, and that created this Silicon Valley. That's all the company HP, and you talk about this making this all the chips because of this Shockley, this semiconductor inventions. All right, and because of that, I think it's you can see the areas grow substantially. All these company has been developed really because of this entrepreneur culture that encourages students and professors and engineers to start their own ideas and create companies. All right, and there's a lot of venture capital funding around here to support these activities, and the growth is substantial. And because of that, you can see that the company we talk about HP and other company now is really not in the top of the rank, but most of the company we're talking about now is talk about Google, Apple, and this company Tesla. As I mentioned, the Tesla electric car company. This Tesla's headquarters is on Stanford campus too. So and you have a Facebooks all around this area. So if you visit next time to Stanford, you will be able to have opportunity to visit all these companies around this neighborhood, with only a few miles away. So I want to come back to the issue that we try to, the conference try to address, which is structural health monitoring. I think the structural health monitoring is really technologies we're trying to look into solutions, the solution that address the industry need for monitoring or managing their assets. All right, managing their assets. That means you like to know your conditions or your structure, your assets, and in real time. So currently, the industry is in so-called third generation, third revolution. We start from in the revolution 1, which is we have the engine, right? Steam engines developed. Then we have assembly line developed, industrial 2.0. And currently we are in a stage of industrial 3.0, which is so-called automation, computers, and electronics. So we produce a very high-end product, high precision product. We design by modeling. We design everything through computations, a lot of modeling. And when also we developed inspection techniques, right? This inspection techniques, so-called NDE, non-destructive evaluation. We perform a scheduled maintenance. We have a constant time, periodic inspect our product. And we have the programming software to control the product, control your system. So the major drivers of the major product in the field, since I'm in the aerospace side, you can see that this is, I consider it's a top crown jewel of the industrial 3.0. So these are the product of 3.0. And you can see the aircraft, the 350, you can see 787, all these aircraft coming because of this industrial 3.0, the high performance product, the design by modeling and design by damage tolerance, scheduled maintenance and programming control. All these are the product and the result of the industrial 3.0, all right? And we have enjoyed this development and tremendously. And one thing is a very crucial and the important part is to remember in order to really look into this, I actually purposely, you can see here, if I use my, since this is Zoom, I normally can use my mouse. Let me see where is sorry, I try to find my okay here. I want to use my where is let's see. I'm going to find my okay. Okay, so I'm going to use my pointer here. You can see here is schedule NDE. All right, this is critical. This is very critical. The reason is on the list of all these items because of the NDE inspections. So to allow these high performance like aircraft to fly continuously. So they are you can see if you look at the next slide. Okay, this inspection is very critical. This inspection will allow the schedule of maintenance, will allow the guideline to create so-called operation. All right, it has the design based on the damage tolerance. Damage tolerance design means on aircraft, when you design the aircraft, you do allow the aircraft to have certain amount of the so-called the flaw or some kind of defect on the material. Then you design through that process, but then you come up with a maintenance procedures and you come out inspection. So every aircraft, for instance, you have to go through certain amount of time in order to have to go through inspections. So that's so-called maintenance. And you have a scheduled maintenance. This is also happening almost all the high precision equipments. You're talking about mining equipments. You're talking about manufacturing equipments. You're talking about automotive. Everything requires maintenance. Right? This maintenance is go with the NDE. So that provides the safety, life cycle cost, and performance all linked together. And as a result of this, and what happening is the industrial 3.0 leads to these divisions. All right, that means in the design and analysis, as we do, we will focus on design analysis, and then once we design analysis finished, we pass that information to manufacturing. So the manufacturing facility will manufacture a product, all right, based on the design analysis. Once the fan manufacture a product, then you send it to operator. Somebody buy the product, then operate it totally different, right? Operate it based on the original design consideration and operate it. Once you operate it, then you have the maintenance person, which is fourth group, to maintain your assets. So these four groups pretty much completely isolated and operate by its own. As a result, the system, the precision equipment is really optimized to a performance. Then as a result, each individual department become very expensive and costly because the design is only focused on design. Manufacturing focus on manufacturing, and operation and services. There's a very limited cross-link and information communication together. So this is the issue of Industrial 3.0. The equipment we are talking about, the machine we are talking about, is high precision, very nice and very, very optimized, but it takes very long time to manufacture. Become more and more challenging to advance, to improve, to go to a higher level, because the processing time, manufacturing time, and the maintenance and service become much longer and difficult. So we used to, probably if you remember, we used to be able to open our car or our automotive car, but to repair our car by ourselves. But now if you open Toyota or even Tesla or electric car, you have no idea what's inside there. All right. So it's very challenging to do this because all become very specialized. So what is the industrial move to the next phase is just coincide with the development of this Silicon Valley was looking for. Silicon Valley was looking for in 2000, early 2007. People have recognized these issues. all right? And we have developed this so-called internet and in the 90s. And then you have this phone developed in the device, so-called smart devices. So people have been predicting that in the future, sensors, network sensor will provide information that throughout the system, your devices, and provide the monitoring, diagnosis, and prognostic information about your surrounding, about all your systems. This kind of concept is coming right in the industry, and through this development of the internet, through the sensors, through information from the data. All right. Now, as you see that currently on the pandemic, this virus situations, it's very challenging to have the human interface interact each other even more. All right. And this has become even challenging, I think, in the future when the system becomes so complicated, so difficult. Now, if you human get out of the loop, that's almost impossible to have anybody to interface, interrogate the system, unless you are actually build everything together at the same time. All right. This is what a high phone is talking about. Phone talk about is we're talking about the system so complicated that it has to be integrated fully, potentially together at the beginning. So this is really come down to a revolution of Industry 4.0. So we were talking about how the system, now you are talking about the very high precision equipments, very high precision automotive, the car, the building, the manufacturing facilities. You have to build this. From when you build this, that information, manufacturing information, design information should be fully integrated in your operation, final product. So this is a so-called cyber physical system. Cyber means it's a communication through the internet, through the data. Physical means it's real product. So there's a digital and the physical system has to integrate together to produce your product. So this is this Industry 4.0. And I'm not talking about this, we are dreaming about this Industry 4.0, which is all the car and robot and the electronics, airplane are flying by itself. And it's actually coming, all right? And if you come to the Silicon Valley, you walk on the street, you drive around, you'll see autonomous car. The car is driving by itself. No humans, no pilots, no drivers, by driving itself. And you'll see a lot of automations will be done by robot, all right? So this is something that is coming up, and more will come in. So this is an industry that in so-called in revolution 4.0, that we are talking about intelligence, we are talking about mobilities, we're talking about autonomous, right? This requires a lot of data communication in order to realize what's happening. And this has to be built from the ground up. That is, your structures, your material should have this kind of capability that include this communication capability, communication to its product to product communication, product to human communication. So robot to human interface, right? The car should be able to communicate with a human. Car should be also communicate with car itself. So this is something that is coming up and definitely need, as I mentioned, sensor data, right? A lot of sensor besides the internet data. You will talk about human sensor data. This is something that, for instance, Volkswagen is one of the biggest automotive company in the world, that in Germany. It is teaming with Microsoft to develop this so-called cloud system. You will wonder why the Microsoft will get into car business, right? And why the automotive company will team up with this PC maker, the software company. This is coming up in the future, all right? The reason is, as we know that the car will be built with in the future, probably all electronics, right? Electric parts, and it's just like a big computer. Everything It's a electronics control and has a software built into it, right? This software will link to your operation, link to your service, link to your all customer wanted everything together. So the car should know the condition of its health conditions, right? The automotive, because there's no driver in the car. So the car must sense there's issues, there's a problem, the need to be repaired, or it has a problem in the coming up and it need to be fixed. So this information, I think, is coming into play that need a sensor has to be integrated with the structure, provide the information so that you can create this the system approach, so-called cyber physical systems. Yeah, and this is a vision of the in the future of the airplane. For instance, Airbus talking about the car like a passenger personal car. You can drive like a car, and then you can fly like an airplane, right? And you can go somewhere, personal devices, and to do that this is something that we are not dreaming about it. And there's in the Silicon Valley, and we have many companies design this airplane, personal aircraft. Is as Google is talking about making this delivery, right? Amazon deliver goods using drone on the aircraft. So again, this kind of devices will require it's a monitoring system, right? It will require the knowledge about what is going on the aircraft and what's going on the system, because it will fly or drive by itself. So this gives you some idea about what is really coming up in the society, all right? So if you look at the value of so-called industrial Internet of Things or so-called smart cities, we're talking about, this is a smart city with all the information connected together. The biggest information we like to know is really how your system operates, how is they are performed, right? You need continuous to monitor this system. You need to continue to provide information about so-called preventive maintenance so that you can project it, how long your airplane can fly, how long your car can drive, and whether you should pass this maintenance schedule and to go to the next. If you think it's based on your current situation, you might be able to avoid that. So this information is very critical in terms of come up with the performance matrix for these autonomous systems. And to do that, I think this is the key component for the Industrial 4.0 to provide this kind of information. And so this is basically, if you look carefully, pretty much we are talking about major component is the structural health monitoring. That whatever you build, you need to know the condition of your structures, your system, almost in real-time basis, the health conditions, the integrity of the conditions, the reliability conditions, all right? So first thing you need to do is a very conceptual design that when we talk about structural health monitoring, is can you build something that like a human? Human is a very best example for structural health monitoring, because human has a nerves built into the structure to can sense what's happening, and then you make decisions, all right? So the sensory system is one of the critical components, which is exactly what's projected by the Silicon Valley, the long time in 2000 projected. This is coming up and growing up in the industry. The sensor, right, the devices, the system, provide the informations. I think what we need to do is to take the data, take the information to understand and make a prediction about what is happening to your structure, to your devices. Yeah. So in terms of structural health monitoring, it consists of the several key components. One is definitely your device, the structures. The other one is sensors. The third one is you need to collect the data from the sensors. then you process the information. Finally, you manage the information. You make a projection in terms of what happens, so-called event detections. You can isolate it, locations, and what happened to the failure severities, and what is your mitigation plan? All right. So this is something that is this aerospace industry has actually led this development quite some time, almost 20 years. So this is actually one of my friends is putting a sensor on the aircraft, and there are a number of different kind of sensors now. Has been tested and tried on the aircraft and for certifications. And one is being certified is a CVM sensor that has been certified, and the other one is a sensor being technology being certified. It's being evaluated. Is a smart layer, is a piezoelectric material, which is we were actually invented from my laboratory and commercialized for industry applications. And we have tested this material on the 787 aircraft when they developed this prototyping. Also on Airbus 350, you can see that we have sensor instrumented on the fuselage of the panel and with the sensors. So this is give you some idea about the development process on these technologies. And currently, we see a lot of application and it's driving in the different industries, from UAV, as I mentioned, aircraft, and the pipeline industry also looking into these issues, and the mining industries looking how can the heavy equipment could be monitored on the remotely, so to minimize the downtime. The high-speed train also could be used to minimize the train derail and other issues. So this is, you can think about a lot of information you can provide it with this concept of the industrial IoT or smart city concept. If you have sensors, and you have different kind of sensors, and that provide information, then you need the interpretation software to understand what's happening on your systems. Then you make a decision from that understanding. And this is the communications, very critical. And you can use cloud computing, you can use edge computing. There's a different approach to solve this problem. So, and to move this technology forward, actually, and actually in 2006, actually I was the organizer and chair the first session of the integrating this industry, and also develop together, create this so-called industrial steering committee for structural health monitoring. We put together of industry companies and universities and also developers together, and try to create this guideline and to help industry to implement the technologies. So we actually published a book, a so-called guideline to implement this technology or industry for commercial aircraft. And there are serious other recommendations and also guidelines are being developed and will be published and become available to industries. I believe this also should be applied to construction industry, to manufacturing industries. The many industries probably need to have this kind of technology standardized in order to have it easier for implementations. All right. So what is this impact of structural health monitoring to this smart city or industrial Internet of Things? Really, I think we can make a structure become condition-based maintenance, right? We can automatically to inspect the aircraft autonomously without the human involved. We can perform this real-time operations, and that is something we can minimize the downtime, and we can provide this so-called safety, life cycle cost, and the performance with the minimum cost to address the autonomous issue, intelligence issue, and the mobility issue for the upcoming smart city concept. So I think the structural health monitoring is really a solution. One is a platform solution for upcoming smart city. right? You have to have a sensors, you have the software, you have a platform put together for your product and devices. So it's involved integrate a multifunctional system. So it's not a product, it's not just making as one component. It actually has multiple components, multiple features. Multifunctional is very key word. So it's the multifunctional of your product. The cyber physical system is a system that has the digital and physical combined together. Finally, I think it has to be real-time interpretation. All right, and a lot of people talk about digital twin. I saw this this 2-day presentation, and many people has talked about digital twin. I think digital twin is really, you have a physical domain and you have a digital domain. How these two domains work together. All right, it's also come out very interesting. So I think this is a 2-day program. I saw very nice the list of the papers there. It's really touched very nicely, all right, in terms of the overall scope of the technologies. So again, cyber physical system is really pretty much is a core technology for this smart city, but which also is really similar, coincide with the technology of structured health monitoring. We are talking about sensors, we're talking about computing, we're talking about the actuations and integration together, all right, communication. So this is very similar. So the digital city, digital twin, I don't have to evaluate again. It's basically it's the digital part and the physical part, how you link together. And to link this together, you have to have a sensor to technology to link this together, which is just like a structural health monitoring. The sensor data will provide information about your devices, the health condition. So I think this is the vision of structured health monitoring. That I think that one day we'll be able to take our iPad or devices, say, hey, I want to look at my car and the left side of the pieces, what happened. You can pretty much using your laptop and pinpoint that and find out what happened in that conditions of your car, your devices, anywhere, anytime. All right. This is not a dreaming. I think this is really industry is moving toward that directions. And I think if you are researchers interested in this area, I think this has a tremendous growth potential in next century. And I hope more people will join this. And there are many things need to be integrated together and to get into industries. So I would like to conclude my presentation basically saying is the structured health monitoring is a platform. It's a platform technology for our industrial 4.0, so-called smart city, for next revolution. So next revolution, health monitoring basically is a part of it. Any smart city, any smart devices has the capability to diagnose or to interpret the health itself, just like a human, right? The human, if we don't know our health conditions, then we cannot make a decision to the next steps. So if we don't know ourselves well, then we cannot make a decision to how to impact the others. So this is a key technology, I believe. So I hope, I wish the conference is very successful, and hopefully I will be able to see you guys in the near future. Thank you very much. So
thank you, Professor. Thank you, Professor, for your nice presentation. So what is Kong?
The questions for this topic? Anybody ask questions for Professor Fukuchang about this topic? I'm curious about smart city because my background is urban planner. In the future, I have a question for you. That Ho Chi Minh City right now, they want to make this city become smart in the future, like your topic. How could we prepare for it with the level of Vietnam? You know, Vietnam is the developing
Yeah.
country. We do not have much more device, I think, facility, but we should prepare from now. Any suggestions for us in particular Vietnam and other developing countries to be ready for next 20 years? Thank you.
Yeah, I think this is a very good question. I think it's a smart city concept. It's not new. It has been coming for some time. I think we all know the automotive car, right? For instance, electric car is coming, and Vietnam has a many huge manufacturing capacity to absorb this fabrication techniques. So a lot of, I believe the new fabrication facility probably will move to Vietnam. So I think there's an opportunity that you should have a chance to support to build these kind of devices. Even electric car, we're talking about some new devices. There's a lot of integrated system will coming in. All right, and the drones, for instance, aircraft, the bridges design. And I know Singapore, for instance, has every building has wireless, not wireless, fiber optics and wireless communication there developed. So this is a city construction business. I think besides that, and the power, the engines, the pipeline industry, the refinery, there's a lot of things can be developed, and the technologies is some of these new technologies doesn't require this it's a brand new a new facility, brand new, I would say, this heavy equipment to produce that. All right, this is a system we're talking about. A lot of sensor technologies, software developments will be integrated. I think this is something you should start thinking about it. In the next 20 years, there's a lot of new systems will be coming up.
All right, yeah, I got your suggestions. I hope Vietnam and other countries could learn from a lot from your presentations. And it's time for the next keynote. But before that, we would like to invite all of you have a photo section so we can have memory of this conference to take home. And the other person who watching us online, don't be worried because we have you on the link on the video. It will be broadcast to all over the world. So invite, please all come to the stage to have a photo together. Uh, because we have a president today.
Mời thầy cô mọi người chúng ta lên chụp tấm hình làm kỷ niệm. Các bạn sinh viên lên luôn đứng nhanh lên. Bạn sinh viên nè, bạn lên đứng sau nè. Nhanh, hurry. Nhanh lên nào.
Okay, thank you very much. Yeah, appreciate it.
Thank you for your appearance. The next special guest speaker today comes from Professor Rakata Rao from the Department of Mechanical Engineering, SV National Institute of Technology from Surat, India. Professor Rao have more than 300 research papers to credit, and especially he have authored he designed a special theory. I hope he will introduce by himself on next presentation. Professor Rao, please.
Oh, thank you very much, the organizers of the international conference. Just I want to share the screen. You may allow me to share the screen. Okay. Yes. Professor Samir Khatir, you are able to see this screen? PowerPoint?
Yeah, it's okay. It's okay, Professor. Yes, we can see.
Thank you. Thank you very much.
Okay, thank you. Thank you.
So the topic of my presentation is structural optimization using advanced optimization algorithms.
Can you just, Professor, make a slideshow, please?
Pardon?
Slideshow.
A slideshow I will make. Actually, there is a reason. Sometimes I may slideshow and sometimes I show like this.
Okay.
Okay. Okay. Okay, if you feel, then okay. All right. It is now in the
perfect. Yeah, perfect. Yeah. Okay, thank you.
Okay, but sometimes I may switch over to the normal mode. Okay.
Yeah.
Okay. Okay, this is all about structural optimization. Many advanced optimization algorithms are being used nowadays for this structural optimization. And so I will try to cover an algorithm that is known as JA algorithm. And I make comparisons of this JA algorithm with the other existing advanced optimization algorithms. And so this is all about that. And of course, you are all knowing about these structures. I am basically a person belonging to mechanical engineering, and we have also some structures, but it is more related with structural engineering. I may not be that much confident in this, but I have seen many researchers in structural engineering, civil engineering, they have applied advanced optimization techniques to solve their research problems. So these advanced optimization algorithms are used for solving these structural related optimization problems. So what is this structural optimization? Let me make a quick recall of this. The process of finding the best or most efficient size of structural elements, size optimization, form for the structure, that is called shape optimization, and connectivity between structural elements, topology optimization. These are called structural optimization. So these are three: size of the structural elements, shape of the structural elements, and the topology optimization. These three topics come under the structural optimization. And during this process, some constraints must be fulfilled. That means whether we do size optimization or shape optimization or topology optimization, definitely we have to face certain constraints, and those constraints must be fulfilled. And the size optimization, if we talk about the first one, size optimization, that size optimization aims to minimize the weight of the structure while satisfying certain constraints on displacements, stress limitations, or both of them simultaneously. These challenging optimization problems have achieved significant attention from numerous researchers, particularly in the last 2 decades. An appropriate optimization algorithm should be taken into consideration to solve these optimization problems. In general, there are two optimization approaches known as deterministic approaches. Deterministic approaches are also known as traditional optimization algorithms. They give exact optimal solutions. The second approach is known as probabilistic approaches. They are also called meta-heuristics. They give approximate optimal solutions. Sometimes they give the exact solutions also, but many times they give approximate optimal solutions. These two are the approaches, deterministic approaches and probabilistic approaches. But deterministic approaches, they have certain disadvantages. They involve high computational complexity, and only limited types of optimization problems can be solved. Only limited types of optimization problems can be solved by deterministic techniques. And complex problems, it is not easy to solve by deterministic optimization approaches. These deterministic optimization approaches are also called traditional optimization techniques. Now, so there is need for these meta heuristics, also called probabilistic approaches, also called advanced optimization algorithms. This is because the structural optimization is complex, and due to the complexity of their search space, those cannot be solved usually using deterministic methods. In contrast, as I said, meta heuristics as probabilistic solvers, they are capable of avoiding local minimum and accelerate convergence, as well as solving the problems at an affordable computational time with acceptable precision. That is why we prefer these meta heuristics, also known as advanced optimization algorithms, for solving the structural optimization problems. And in recent years, structural optimization with meta heuristic algorithms has been very popular among the researchers in the structural engineering field, particularly genetic algorithms, evolution strategies, particle swarm optimization, PSO, ant colony optimization, ACO, firefly algorithm, cuckoo search, harmony search, teaching learning based optimization, and big bang, big crunchy. You see, still there are many algorithms, but these are some of the important algorithms which are found for this structural optimization. And they stand out as the well-known optimization algorithms which have been highlighted in some of the research papers and monographs. And now we have many powerful computers, and searching for optimal solutions to engineering design problems becomes easier now. So many researchers are still developing advanced optimization algorithms, and the competition for the most efficient advanced optimization algorithm continues. As I have told just now, these are many advanced optimization algorithms. These are only few which I have written here, which have been applied in structural optimization. But there are a few more algorithms also applied for structural optimization. And in general, if we talk, then dozens or tens of advanced optimization algorithms are available in the literature. Then the question is, which is the most efficient advanced optimization algorithm? So that question remains. So the research is evolving. Researchers are still proposing some advanced optimization algorithms, and they claim that their algorithm is working better. But in general, my opinion is no algorithm is perfect, and no algorithm can solve all types of problems. We are human beings. As we are human beings and we are not perfect, so we cannot expect these algorithms to be perfect and applicable for solving all types of problems. But if our problem, once we have one structural related optimization problem, and we apply, say, 5 optimization algorithms, out of which we know 5 optimization algorithms. So we applied those 5, and one of those optimization algorithm is giving better solution for our problem. Then we consider that particular optimization algorithm is the best for this problem. For this problem, we cannot generalize that particular optimization algorithm is the best for solving any type of optimization problem. So this point we should keep in our mind. So the search for the most efficient advanced optimization algorithm, it continues, but we have to realize there is no such perfect algorithm which suits to all applications. Where depending on our application, whatever optimization techniques we know, we apply all those techniques on that problem, and whichever technique is giving comparatively better solution, that we accept as the best optimization method for that problem. In this presentation, a simple and efficient advanced optimization algorithm for structural optimization is explained, and that is named as J algorithm, which I have shown here. All the evolutionary and swarm intelligence based algorithms are probabilistic algorithms and require common controlling parameters like population size, number of generations, elite size, etc. So these advanced optimization algorithms, they have certain parameters which we have to tune so as to optimize our real problem. So what are those parameters of these optimization algorithms? Some common parameters are known as population size. That means population size is with how many initial solutions you have started with. How many initial solutions you have started with. And number of iterations, how many generations, also called how many iterations. So these are common for any algorithm. For any population-based advanced optimization algorithm, this population size and number of generations, these are common. Common means every algorithm requires these. But besides these common control parameters, different algorithms require their own algorithm-specific control parameters. For example, if you take the very famous genetic algorithm, there we have algorithm-specific parameters like crossover probability, mutation probability, selection operator, like that. So if you take different values of crossover probability, mutation probability, and the selection operator, we may arrive at different optimal solutions. Then the question comes, what is the optimum set of these crossover probability, mutation probability, and the selection operator of genetic algorithm that will give the real optimum solution of our problem? So that tuning, adjusting those parameters is required. That is a burden on the designer. Similarly, other optimization algorithms, PSO, ABC, whatever, those algorithms, all those have their own algorithm-specific parameters which require to be tuned. So that is an extra burden on the designer. Considering this fact, this J algorithm was introduced in 2016 and it does not require any algorithm-specific parameters. Hence, the burden on the designer to find the optimum values of the algorithm-specific parameters is reduced, and our effort will be to find out the optimum values of the variables of our problem. Okay. Now, the J algorithm requires only common controlling parameters like population size and number of generations for its working. As I have already explained, that any advanced optimization algorithm, any population-based advanced optimization algorithm requires this population size and number of generations. So J algorithm is also requiring these, but the algorithm-specific parameters it is not having, so that we need not to tune those algorithm-specific parameters. So the burden is reduced on the designer. So the J algorithm has gained wide acceptance among the structural optimization researchers. It is comparatively simpler to apply. This is the advantage of this method. This is simpler. One can easily understand, unlike other advanced optimization algorithms. Here is actually the equation, the single equation, which is the simple equation of this J algorithm. Actually, this brings good results. What is this? If fx is the objective function to be minimized or maximized. Now, our objective function in structural optimization may be minimizing the weight of the structure, minimizing the weight of the structure. So at any iteration I, if we assume that there are m number of design variables, here design variables in our sizing optimization, design variables are like cross-sectional areas of the members, cross-sectional areas of the members. Those can be taken as design variables. And n number of candidate solutions. That is, so how many members are there? So like that we can correlate. I will show you that by means of an example. Here, how we modify the values that is given by this equation. I show you the flow chart. By means of this flow chart, you can understand. Initially, we decide the population size and the number of design variables. Population size, as I explained, it is the number of initial solutions we start with, some randomly generated initial solutions. Number of design variables we decide, how many variables are there, 5, 10, 12, 13, any, depending on your application. And termination criteria. We decide after how many iterations to stop this running of this program. Then we identify the best and worst solutions in the population. Best solution and worst solution we identify. Then we modify the solutions based on the best and worst solutions. This is that equation which I have explained. Then we compare the new solution with the old solution. If the new solution is better, yes, accept and replace the previous solution. If new solution is not better, then we keep the previous solution, we reject the new solution. Then we check, is the termination criterion satisfied? If it is no, then we go back, and that is called second iteration. During second iteration, again, we identify the best and worst solution. This procedure continues. Once this termination criteria is satisfied, then we report the optimum solution. This is the flow chart of this J algorithm. And now I explain by means of an example. Suppose our objective function in our structural optimization, objective function is minimization of weight. Let us say, just to demonstrate this J algorithm, I have taken one minimization function. This is sigma xi square, I equal to 1 to n, and the range of variables minus 100 to 100. The variable can take any value between minus 100 to 100. This is a standard benchmark function. For this, the solution is already known, that is 0 for all xi values of 0. If there are two variables, then x1 is 0, x2 is 0. Then fx will be 0. If there are three variables, then x1, x2, x3, all three will be 0, and fx is 0. That is a known solution. So this benchmark function, now I am using to demonstrate the working of this J algorithm. As per the flow chart, we have generated 5, we assumed population size as 5 initial solutions, randomly generated. We have assumed two variables, x1 and x2. Only two variables I have taken for demonstration purpose. These can be any number of variables. Then fx is, if we take two variables, fx is here, sigma xi square I equal to 1 to 2. So that is x1 square plus x2 square. So minus 5 whole square plus 18 square equal to 349. So these are randomly generated values. You can see these x1 and x2 values are randomly generated, and they are within the given range of minus 100 to plus 100. Minus 100 to plus 100. They are randomly generated. Now fx values are calculated based on these x1 and x2 values. Now as per the flow chart, what is flow chart? We have initialized the population size 5, number of design variables 2, and termination criteria, it is up to us. Maybe after 100 iterations we may stop, or we will see. Then identify the best and worst solutions in the population, then modify the solutions based on best and worst solutions. So how we do that? Now we have randomly generated these, population size is 5, and fx values are calculated, and it is minimization problem. As it is minimization problem, so whichever is the minimum, that is considered as best. So 113 is the best. So best x1 is minus 8, best x2 is 7. And worst, whichever is higher of these fx, that is considered as the worst. So 4936 is the worst. So worst x1 is 70, worst x2 is minus 6. Then we modify. This is table 1. So table 2 will contain the modified values. How we do that modification? That is this simple formula here. X new value equal to old value plus some random number multiplied by best value of x minus absolute of that old value minus second random number R2 multiplied by worst value of x minus absolute value of old. So by following that, what we have done, so what is the new value of x1 for the first candidate? That will be this minus 5 old value plus some random number between 0 to 1. Random number is random between 0 to 1. Any value between 0 to 1. So this old new value equal to this old value minus 5 plus random number multiplied by best x1. Best x1 is minus 8 minus absolute of this old value, then minus R2, another random number multiplied by worst value of x, 70 minus of absolute minus 5. Similarly, if you take if we calculate the new value of x2, That will be this old value 18 plus random number 1 multiplied by this 7 best value minus absolute of this 18 minus random number 2 multiplied by worst value minus 6 minus of absolute 18. That will give the new value of x2. So that way, actually here I have explained all that procedure. This is for x2 old value plus some random number multiplied by best x2 minus absolute of old value minus random number 2 multiplied by worst value of x2 minus absolute value of that old one. So that is giving the new value of x2 as 19.64. Similarly, x1 new value minus 65.19. So that we have kept in table 2. Table 2. New value of x1, new value of x2. So that fx is now this x1 square plus x2 square. That is fx. So with all the new values, like as we have done for the first candidate, for the second candidate also we find the new values of x1, x2. For the third candidate also, for the fourth candidate, for the fifth candidate. After doing that exercise, we are having these values. We are having these values. So now, as per the flow chart, whatever flow chart is showing after modifying the solutions based on best and worst solutions, we have to compare the new solution with the old solution. If the new solution is better, then we accept the new solution. If it is not better, then we keep the old solution only. So now table 1, then after modifying this is table 2. Now these table 2 values are compared with table 1. This 4635 fx is compared with this 349, old value 349. As it is our minimization problem, so 349 is better. So we take this combination forward, to table 3, Then old value of second candidate is 4165. The new value is 3997.7. So new value is better. So we take this set to table 3, next table. Then what is the new value for the third candidate? 613.697. And the old value is 4936 for the third candidate. So new value is better. So new value we will take up. Old value for fourth candidate is 113. So here new value is 4735. So old value is better. So old one we will take. Fifth candidate new value is 5249. And here 468 for the fifth candidate. So this is better. So this we will take to the next table 3. So after doing this, we have this table 3. So this is our the updated values of the variables and the objective function based on fitness comparison at the end of first iteration. First iteration is over. At the end of the first iteration, we have best as 113 and worst as 3997.7. Then if we do the second iteration, that is second iteration, so what is the flow chart showing? Is the termination criteria satisfied? No. Then we go back and then we identify the best and worst solutions and the procedure continues. So the same procedure we will continue. Here best is 113, worst is 3997.7. So best x1, so best x2 and worst x1 and worst x2 we have identified. Then assuming some random numbers between 0 to 1, we go ahead and then we prepare this table 5. So these are the new values of x1, x2, modified values, new values of fx. Then these new values of fx are compared with these old values of fx. Whichever are better, we are taking forward to table 5. So this is the table 5. Updated values of the variables and the objective function based on fitness comparison at the end of second iteration. We can see after 2 iterations, the best value is 7.78. Initially, when we started random solutions, then the best value was 113. Now, best value is very much reduced. Ours is minimization problem, so the reduced values are better. So algorithm is reducing this value of fx. That means algorithm is working well. Similarly, the worst value also, you can see it is improved. Initially, it was very high, but now it is 2381 only. So if you do more iterations, this is the end of second iteration. Then at the end of second iteration, we have best here, then best x1, best x2, and worst x1, worst x2. Assume some random numbers for x1 and x2, go ahead. Then after few iterations, you will get all fx values as zeros and x1, x2 as zeros. That means the known solution is achieved. For this benchmark function, known solution is 0. So after few iterations, you will get that value. So this is the way how this J algorithm is working. This is the basic J algorithm, which was originally initially developed in 2016. Later, many researchers have made many modifications to this J algorithm, and they are successful, and I welcomed all those modifications or improved versions of J algorithm. And now we can see the applications of J algorithm for structural optimization. And many researchers have applied this J algorithm for structural optimization. Certain applications I have listed at the end of this presentation. But now for demonstration, just to give you a feel of this J algorithm, how it is applied in structural optimization, I have taken up two research papers published by researchers, and that I issue. Structural optimization, the objective function, variables, and constraints. And this was attempted by Dagertekin and others in 2018. So the objective of truss optimization is to minimize the weight of the structure under design constraints, such as element stresses and nodal displacements. The sizing optimization problem of a truss structure is stated here. The minimization, this is minimization of minimizing the weight. And here this is the density of the material, and it is cross-sectional of the member I, and similarly the L is the dimension, and this is actually the length of the member. Li is the length of the member I, Ai is the cross-sectional area of the member, and gamma I is the density of the material. So this is nothing but our weight. So minimize, here our objective function is minimizing the weight. I equal to 1 to nm, where nm is number of members. And this is subjected to certain constraints. That is stress in the member, sigma I, that is between the allowed values of some compressive stress and tensile stress. Compressive stress and tensile stress. And the delta G is the displacement at the node. The displacement is specified, some minimum value and some maximum value. So the displacement at the node should be between this minimum and maximum. And this is AK is related to the cross-sectional area, and that also specified some minimum value and some maximum value. It should not be more than this A max, it should not be less than A min. So these are the constraints related to stresses, displacements, and depending on the if minimum area, if the cross-sectional area of a member is less than this A min, then we delete that member from the structure. Then that thereby we decide the topology. Topology optimization is related to that, where cross-sectional area is of a member is less than the minimum A cross-sectional area required, then we delete that member from our structure. So that way we achieve the topology optimization. So this is what explained here. Then what is layout? Layout optimization. Here for optimization problems including layout variables. Then here not only the weight, but here coordinates of the nodes. Those are also considered. That is what this equation is like this. That is here material density and cross-section area of the member. Then these coordinates. These are the coordinates of the nodes limiting the ith element of the structure. Optimization problem includes design variables, including the cross-sectional area sizing variables and layout variables. So total number of variables will be equal to number of sizing variables plus number of layout variables. And in topology optimization, elements can be removed from the structure if their cross-sectional areas become very small. For example, 10 to the power minus 7 inches square. So then some penalty function is applied here. If any constraint is violated, if any constraints are related to stresses and displacements. So if any constraint is violated, then how to deal with that? These authors had proposed certain procedure. This is the summation of stress penalty. This is for stress penalty, and this is for displacement. Equation 5. Phi delta J indicates the displacement penalty, and phi sigma I that indicates the stress penalty. They have explained that procedure. And when the stress in the member is between compressive and tensile stresses, given compressive and tensile stresses, or acceptable compressive and tensile stresses, then no violation, zero, no penalty. But if it is not so, then some penalty is applied like this. If displacement of the node is between the allowable delta min and delta max, no penalty. But if it is exceeding, that is delta G exceeding delta max, or delta G is less than this delta min, then there is some penalty. So this way they have applied. And now they consider planar 200 bar truss with elements grouping used in optimization. So this is a 200 bar truss having 77 nodes. 77 nodes it is having, and number of members 200. But here these are all grouped. 29 groups these are made. Like 1, 2, 3, 4. You can see 1, 2, 3, 4. So their cross-sectional areas are same. 1, 2, 3, 4 cross-sectional areas are same. So they have grouped them as one. Similarly, 5, 8, 11, 14, and 17. 5 is here, and 8 is here, 11 is here, and 14 is here, and 17 is here. So those are all having same cross-sectional area, so they have grouped them as 2. So that way they grouped into 29 groups are made, and these 29 are considered as the sizing variables. 29 design variables are here, and then the comparison of optimized designs for 200 bar truss problem. As I said, 29 groups are there, 29. So those are considered as the design variables. These are cross-sectional areas in inches square inch. And different optimization algorithms have been applied for solving this standard benchmark structure. And like this is depending on a simulated annealing. This is artificial bee colony algorithm. This is some hybrid harmony search based algorithm. This is TLVO algorithm, and it is swallow swarm optimization, some hybrid PSO and swallow swarm optimization, flower pollination algorithm, and water evaporation algorithm. So various researchers, they had attempted the same problem, and they suggested the weight of that 200 bar planar structure as this. And whereas these researchers, Jagartekin and others, they applied genetic algorithm. They found the weight as 25,463.53. Whereas these other values, those are more than that. So the minimum weight is obtained by this J algorithm, and the cross-sectional areas of those groups of members are calculated like this in a square inch. And yes, here it is related to in how many function evolutions this has achieved this result. That is it. And statistical performance, if you do all those algorithms, the standard best weight is obtained by J algorithm. Even average weight, if we run that program many times, 20 runs, 30 runs like that, these peer authors had run it 20 times. The average result is here. And worst weight means the maximum weight which they obtained for this is this. Then standard deviation is 24.12. And you can observe all these values are better than the values given by the previous algorithms. And CVP is related to any constraint violation. Here none means no constraints are violated. So this way we can understand, and this is the convergence graph, how this algorithm is working. This convergence means it has reached the optimum solution in less number of iterations, and number of structural analysis. This is equal to the population size multiplied by the number of iterations. When that is plotted here, you can understand this genetic algorithm that has achieved good convergence. The second case study related to spatial 942 bar tower. It is containing 59 design variables. This is a three-dimensional view. This is the side view, and this is the top view. And the total number of bars 942. This is considered as a medium-sized problem, medium-sized optimization problem related to structures. Here also, various optimization algorithms um, have been tried, like genetic algorithm, simulated annealing, evolution strategy, some genetic algorithm combined with Nelder-Mead simplex method, cuckoo search, and firefly optimization algorithm. And JR algorithm has given the minimum weight. You can see out of all these weights, this minimum, this is the minimum weight. This is the minimum weight. And similarly, when they run that program many times and then taken the average weight, this average weight is also better than these. These other algorithms, they had not mentioned what is the average weight. So this data is not available. So similarly here, standard deviation is also less. The less standard deviation, the better. And here, no constraints are violated. And if we take the large size problem, a spatial 1938 bar tower containing 204 sizing variables. You can see here, and this is the top view. And when you observe this, the researchers had applied various optimization algorithms like this, and the JR algorithm result is given here. This is the tons. The weightage is in tons. Weight of this 1938 bar tower. The weight is 99.255 tons using JR algorithm. And the other algorithms have given slightly more values. That means these are the weights of that tower, but weight given by genetic algorithm is less. And so this is considered as the good algorithm for this problem. And similarly, the convergence graph, if you see, the JR algorithm that has converged very nicely as compared to other optimization algorithms. Then Covey and others in the very latest paper, they considered a 3-bay 24-story steel frame, 24-story steel frame, and we are having 3 bays. And this is containing 96 columns and 72 beams. And they are made into 16 column groups and 4 beam groups depending on their cross-sectional areas. And then these are the results. Harmony search algorithm results, evolution strategy combined with differential evolution, water evaporation optimization, similarly cuckoo search. And these people, they applied some modified version of J algorithm, and they had shown that J algorithm has given the minimum weight as compared to the other optimization algorithms. And the standard deviation also less as compared to other methods. So this way, this can be applied, the algorithm can be applied for sizing optimization. If we take the layout optimization, spatial 25 bar transmission tower with 3 elements grouping, this is grouped into 8 groups here. And here layout optimization means the coordinates are also to be optimized. Coordinates of this fourth node, coordinates of fourth node, that is x4, y4, z4, and here it is, you can see x4, y4, and z4, and x8 and y8. These coordinates, these positions of those nodes, fourth node and eighth node, the positions are important in addition to the cross-sectional area of the members. So they have optimized considering 8 sizing variables and 5 layout variables, total 13 variables. And different optimization algorithms are applied. And the present study has given the minimum weight, 53.049 kg. This way, you can see there are applications of this J algorithm for sizing optimization of structures, layout optimization of structures, and the same researchers had attempted topology optimization also, but I have not included that here. And they had proved that topology optimization also can be achieved using this J algorithm. And I am listing here few research papers that have used this J algorithm. latest works on structural optimization using J algorithms and its variants. That means basic J algorithm that was developed in 2016. After that, hundreds of research papers have been published by various researchers in different fields of science and engineering. So in structural engineering also, some researchers have taken up this J algorithm and they have either applied directly or they have modified that J algorithm and improved its performance. And those improved versions are better. And so I have listed some of the structural engineering related applications of the J algorithm and its variants, like this Covey and others. Improved shuffled J algorithm for sizing optimization of skeletal structures with discrete variables. Then second reference, Ding and others. Non-probabilistic method to consider uncertainties in structural damage identification based on hybrid J and tree seeds algorithm. They have combined this J algorithm with another algorithm, tree seeds algorithm. They hybridized it and they have. And this was published, yes, 2020, this year. Okay. Then Osterk and others, optimum design of reinforced concrete counterfort retaining walls using TLVO J algorithm. And yes, Khatir and others, they have published improved ANN technique combined with J algorithm for crack identification in plates using XIGA and experimental analysis. And yes, same researchers, Khatir and Wahab, a computational approach for crack identification in plate structures using XFEM, XIGA, PSO, and JR. And this Dagger taking Lamberti and Ugier. Discrete sizing layout topology optimization of truss structures with an advanced JR. And Ding and others, structural damage identification using improved J algorithm based on scarce regularization and Bayesian inference. And Kong and others, prediction of long-term temperature effect in structural health monitoring. Our conference is related to structural health monitoring. Here you can observe last year in 2019, Kong and others, they had published a research paper using this J optimization algorithm and the Solve Swarm optimization algorithm. They predicted the long-term temperature effect in structural health monitoring of concrete dams using support vector machines with J optimizer and Solve Swarm algorithms. And Dagertekin and others, they have attempted the sizing layout and topology design optimization using J algorithm. Bekdas and others, transfer function amplitude minimization for structures with tuned mass dampers considering soil structure interaction. Here also they have used J algorithm. These are the latest two applications, some of the latest applications of J algorithm and its improved versions in structural optimization. So with this, what I can say, even though I am a man of mechanical engineering, but as these optimization techniques can be used in any field of engineering and science. I have found these civil engineers, structural engineers, the faculty members of structural engineering, they have applied this J algorithm to solve their research problems. And so these are some of the papers. So what I appeal to the participants of this conference, if your research problem is involving optimization, then you may try this optimization algorithm, which I have proposed now, known as J algorithm. Of course, I am not forcing any of the participants, you apply this only. There are many optimization algorithms available. But this algorithm, what I can say, this is a simple algorithm to learn. And at the same time, it works satisfactorily. I don't say it is the perfect algorithm, but it has given good results in majority of the applications in different fields of science and engineering. Researchers are reporting that. So if you feel interested, then you may apply this J algorithm in your structural optimization problems. With this, I want to say thank you very much for the organizers and participants of this international conference. Thank you.
Thank you, Professor Rao, for your theories, I believe your theory, your methods could be applied not only in the construction industry, but also will be applied into the social life and economics and also in the finance.
Yes.
Your theory very new to us. We are very happy to
Thank
listen to you almost nearly 45 minutes. Actually, it's very headache to us, but we are very excited to listen to your talking, to your lecturing.
thank you. Thank you. Thank you.
Uh, and next time,
Sir,
like to have a
can
few
you please let me know to ask some questions, please?
Yes, you can.
yeah, we will.
Yeah, Professor, thank you very much for your nice presentation. So I will try to ask some questions about some created optimization technique recently.
Mm.
So I know that I did a lot of publications using Jaya algorithm. For me, I agree with you. So the algorithm, it's good optimization. It's very fast and also can support a lot of parameters. But I have only the strange question for me. So some researchers, they use some benchmark example, but the number of design variables selected, it's a very low. And they mention this algorithm, it's better than the others. But when I use the selected or the best parameter mentioned in some publications for sexual health monitoring, I detect that this algorithm, it's not good. I don't know. I don't know how can we select the best algorithm for your case. Okay, you use some example using more than 200 elements or at
200
least
design.
different number of variables. I think it's okay, but what about for the number of variables selected for some benchmark example and for complex structure? So is the same or are different or?
And here, actually, as I said, we cannot say that which algorithm works better for our optimization problem. We have a research problem. We want to solve that research problem, and we are looking for the particular. We are looking for which optimization algorithm is better. And as such, there is no hard and fast rule that particular algorithm is the better for this problem. What we have to do is we have to see what is the computational complexity of the algorithms. And if we go through the literature, already some information is available on the performance of the existing optimization algorithms. We can have the idea which algorithm may be better in a particular situation. But my suggestion to the researchers is always you try to learn some for a few optimization techniques and apply all those optimization techniques to the same problem, and then you see the difference which algorithm is working for you. And but if researcher asks me, I don't want to learn 4 or 5 optimization algorithms. I want to learn only one method. So you suggest me. Then my reply is, then you go for the algorithm which you can understand easily, and you learn that algorithm, and you apply that first, and you see whether that algorithm gives good results or not, or not. If you are satisfied, then it is okay. But if you feel that algorithm is not giving good results, then you have to learn another algorithm. And this J algorithm, why I am saying this may be attempted because this is only single equation, which is simple to understand. The modification is also simple. New value is equal to old value plus some random number multiplied by best minus absolute old minus another random number multiplied by worst minus absolute old. Simple equation. Yeah, and I hope anyone can easily understand. But whether this works for large sized problem, for involving a large number of variables, yes, even though I was the developer, I had not attempted such a large number of design variables. Large number of design variables. Of course, I attempted up to 500 variables, but that also on benchmark functions. benchmark functions, mathematical benchmark functions. Whereas these structural researchers, they had taken up some benchmark functions in their structural engineering. This large sized problem, 1938 bar tower problem, that is considered as the large sized problem in structural engineering. So they had applied and they proved that this J algorithm is working. So the researchers, there is no such rule that particular algorithm works better for this problem. There is no such. What we have to do is we try to learn 4 or 5 algorithms and we apply and we see the results. And if a researcher is not interested to know many algorithms, then my suggestion is always learn a algorithm which you feel simple and easy to understand, apply that, and you see whether that works.
Right. We still have one more question people here. If you summarize your answer.
Let's just, yeah.
Yes.
Yes,
Okay,
now
Professor Rao, Gong. Okay.
Nguyễn Phú Cường, member of Faculty of Civil Engineering, Ho Chi Minh State Open University, will have one question for Professor Rao. Please. Professor Rao, thank you very much for sharing our very simple, effective algorithm. I am very surprised about your proposed algorithm because I see as flowchart usual, it's very short and very simple comparing with many another algorithm is GA, micro GA, I know. But I have some question. Could you sharing the limitation of Java algorithm? Which problem we can apply for the bad result and which problem is have not good result? Can you sharing that issue? Thank you.
Yes.
Professor, would you hear?
Professor Khatir, can you repeat that question in your words?
Could you share in some weak point of Java or algorithm and with problem? As you know, in real work, we have many field, mechanical, economic, and education, and we have many problems we can solve. But I want to you share some weak point of Java or Java algorithm do not have weak point. Thank you.
Okay. And these JA optimization algorithm, these codes are also made available on Google sites. One can, these programs are written in MATLAB, and one can download these codes of this JA algorithm for constrained optimization problems as well as unconstrained optimization problems. And in Google sites, it is given. If you simply type JA algorithm in Google, then you will come across that site, and one can download the codes of this J algorithm. And in addition, so much of literature is available on this J algorithm. And if the organizers want any files from my side, you can ask me through email. I will send the files, and the same files can be distributed to the participants. They can be made available to the participants. Thank you very much. Thank you.
Yes, thank you.
Professor, just for me, I'm also interested by the CPU time. So what about for the CPU time? You see, like Jaya algorithm, it's very fast for me. You see that the Jaya algorithm has only one equation and it's very easy. But the problem for me, I have to select the best algorithm also based on the CPU time. But many researchers, they do a comparison with the other optimization techniques, and they select that this algorithm, it's okay, it's good. But what is your opinion? So we should study the CPU time or not for the optimization techniques?
So nowadays we are having powerful computers. So CPU time nowadays is not the main criteria. Definitely, we have to consider the CPU time, but that depends on the problem. If our problem is, if it is taking hours and hours by particular optimization algorithm, then we may think of the algorithm which takes less time. But nowadays, the problems which we normally take up, those are not very, very large size, like containing 1 million variables or 10 million variables. And if really that type of problems are to be solved, 1 million design variables or 10 million design variables, then we can think of what is the CPU time taken by the algorithm. But otherwise, in normal situations, and we don't come across that type of very large sized problem. But if very large sized problem comes, then we may think of if it is taking hours and hours of operation of computer for executing a run. But what I have seen in this Jaya algorithm and whatever I developed recently, very recently, 3 more algorithms I have developed. Those are our algorithms. But if we talk about this Jaya algorithm, I found that it is converging faster as compared to other algorithms. But I am saying every researcher, every developer claims that his algorithm is the best. But I am not of that kind. I never claim that J algorithm is the best algorithm. I say that it is one
No,
of
no,
the.
because for me, I did some applications. I did the professor some applications.
Just only 1 minute. Just 1 minute. So if we are, if our problem is very complex, it requires hours and algorithms are taking hours and hours of operations. Then yes, then we will think about one algorithm which can give us some medium, somewhat acceptable solution within the allowed time. Otherwise, we need not bother about CPU time. And at the same time, I add here this J algorithm and the secret we have to still explore, that is converging very faster to the optimal solution, and that is not local optimum also. It is global optimum. So that is the thing. Okay, thank you.
So the last question, please. The last question, because I have some question related to optimization techniques. So, Professor Rao, which parameter can affect the results to get more to get the best conversions? Which one? I mean, the number of iteration or the number of population size. So, which one can affect, or which one can give good results?
Here, actually, we have tried different population sizes and different number of iterations. And the examples which I have shown in these slides, that sizing and layout optimization attempted by Daguerretekin and others, and you will be surprised that they had produced the results that this population size has not affected their results. They had given in their appendix of their paper, they mentioned population size effect is not much. That is what they had produced. Of course, it was a pleasant surprise to me also, because I have not experimented many. I have experimented only limited number. So they had presented that result. So the algorithm, probably it is converging faster because of that equation. In equation, we are taking that best value minus of absolute old value. That absolute value is taken just with the idea that more exploration can take place. And that minus R2 multiplied by worst minus absolute old, that term is indicating how much the solution is moving away from the worst solution. Plus R1 into best minus absolute old, that is indicating how much close it is moving to the best solution. So it is moving very close to the best solution, and at the same time it is moving very far away from the worst solution. That random numbers R1 and R2, they are also playing the role in this. This is what I feel. Still we can explore it much more.
Yes, thank you, Professor Rao.
Thank you, Professor.
Yes, now, very thank you for your interesting answers all the question of the participants. And now the time for break. After, because it's too late, so the time break only 5 minutes. And thereafter, we will start with Professor Nguyễn Trọng Phước will chair the sections optimization and machine learning for engineering structures. Yes, thank you so much.
Thank you.
Okay, thank you, Professor Rao. Thank you. Huh?
Thank you.
Thank you, Professor.
It is 11 a.m. here, so we will be back in another 5 minutes to have a new section, section 1, optimization and machine learning for engineering structures. The chair will be Professor Nguyễn Trọng Phước, the head of the Faculty of Civil Engineering, and we will have 1 hour and a half from until 12:30. It will be 5 or 6 papers we will present. Please be ready in another 5 minutes. Thank you. Hi, this time for the first section, all of the presenters, please in ready. Professor Fu, are you ready now? So we could start from the first paper, please.
Okay. Hello everybody.
Hai máy hay sao á?
Cái loa.
Nói cái gì đây? Nói tiếng này. Hello everybody. Now, this is our session. First session of SHM and AS. Now, I am from Faculty of Civil Engineering, Ho City Open University. Okay. According to the timetable, the session one, the name of session is application and machine learning for structure. Now, this session has six presentation. The time duration with we have 1 hour. So I would like to invite the first presentation, the number of 181, the application of multiple linear regression and artificial neural network to predict the conversation of different countries based on the internet book with the group authorial of Lê Thắng Vương, Lê Cung, Nguyễn Đình Sơn. Please. Có điện thoại kìa.
Please, Doctor.
Hello. Oh, sorry for the.
Hello. Yeah, Dr. Vương Lê Thắng, Lê Cung, and Đình Sơn, the author of the paper 1081. Are you there?
We have 1 minute. I would like to invite group of Dr. Lê Thắng Vương, Lê Vương Thắng, Lê Cung, and Nguyễn Đình Sơn. The paper number 81. The title of presentation number 1: application of multiple linear regression and artificial neural network to predict the convection different coordinates based on ultra-bull velocity.
We will in the next and after we will go back.
Right. Now, the paper number 81 is absent. So that I would like to invite the next presentation. The next presentation is the paper number is 24. The title of optimization of process parameter primary phase particle size of cooling slot process for semi-crystalline of ADC trail alloys. Mr. Nguyễn Tuấn Anh, Mr. Nguyễn Anh Tuấn, please. Đào Văn Lưu and Giang Lai Đa. Mr. Nguyễn Anh Tuấn, you online? Yeah.
Dr. Nguyễn Anh Tuấn, are you there? Could you hear me? And you can share your screen to present. Let's say your PowerPoint. You select share screen. Yeah. Ông này Iran. Anh nói nè. Yeah, Dr. Nguyễn Tuấn Anh. Are you there? Well, can you answer me?
Yes. I can. You can hear me.
Yeah, I can hear you.
Yeah. My name is Tuấn. I'm liquid from university.
Okay, Mr. Nguyễn Anh Tuấn, are you ready?
My present is third. My present is third.
Dr. Nguyễn Anh Tuấn, please.
Yes. Yes.
Are you
Please,
ready to presentation? Okay. Okay.
yeah.
Yeah, yeah.
Can you see me?
Yeah. Yeah,
Yeah.
I see.
Yeah.
Yeah, yes. Why I cannot hear the no sound?
Oh, no.
You turn on your
Yeah.
volume.
Yeah.
I didn't hear anything. I don't hear anything.
Cái này.
You have any problem in connection?
You will see. I see my presentation.
Yes.
Yeah. I would like to present my presentation.
Now, we see your screen. Dr. Nguyễn Anh Tuấn, please. Can you presentation now?
Yes, Dr. Nguyễn Anh Tuấn, are you there? Can you start your presentation? Yes, Dr. Lê Xuân Lưu, are you there?
Yes.
And now we start with the paper with the number 1043 from Dr. Lê Xuân Lưu. Thereafter, when we finish, we will back with the presentation of Dr. Nguyễn Anh Tuấn after. And now Dr. Lê Xuân Lưu will present the papers with the title Estimations of the Cable Tensions with Unknown Parameters using Artificial Neural Network. Yes, now Dr. Lê Xuân Lưu, please.
First of all, good morning, everybody. My name is Lo, and I come from University of Transport and Communications. So I'm doing a PhD in Japan right now. So because of time limitations, I'm going to share the pre-recorded videos. So can you hear? Dr. Kung,
Yes.
can you hear the
Yes.
sound?
Yes.
Yes, right. Okay,
Yes.
let me start from beginning. Please, here is my presentation.
You saw the video, but in your video there's no sound. Can you,
There's no sound. Okay, so I think we have the same problem as the participants. So let me check this one. I will also open the speaker from my side and check that if you can hear, it's perfect. So here is introduction. It's okay. Target structures are cables in cable bridge, and as you know,
Yeah, it's okay. It's okay. It's okay.
It's okay. Okay, let me start from beginning. Okay.
Yeah. Can you repeat?
Okay, please. Good morning, everybody. My name is Lê Xuân Lưu. I come from Vietnam, from University of Transport and Communication. So today I would like to share my study. The name is Estimation of Cable Tension with Unknown Parameters using Artificial Neural Networks. So the contents is divided into five sections from introduction to conclusions. So here is introduction. Our target structures are cables in cable bridge, and as you know, there's cable plays important roles in terms of cable bridge, and the cable tension must be measured correctly during the construction or the long-term health maintenance. So in order to identify cable tension by vibration methods, first of all, we will measure natural frequency combined with the cable properties, and using some formulation from the vibration theory of cables, we can identify cable tension. There are some previous studies has been conducted based on torque string theory and beam string theory. So in torque string theory, cable mass, length, and measure frequency. And in beam string theory, cable bending stiffness is considered. So cable sag in somehow will be considered in torque string theory and beam string theory. So recently, one of the co-author in my study, Dr. Jabaf, he proposed an application of artificial neural networks for identification of cable tension. So in that study, this author proposed the fixed end cable models with the finite difference model of cable. So, but the problem is for existing cable, the cable bending stiffness is unknown, and the cable boundary condition is also unknown, and therefore in this study we propose a solution to identify cable tension with unknown cable bending stiffness and unknown boundary conditions by using the application of ANS. So to get this aim, there are some objectives like this. First of all, I would like to give a brief introduction about the ANNs. So ANN is nothing, but it will contain an input layer, output layer, and several hidden layers. So the signal will be transferred from input layers to the output layer through activation functions. And in this study, the activation functions is the sigmoid functions. So I'm showing here a finite difference model of cables with rotational restraints at the cable ends. A cable is discretized in an internal node, and with the EI here is bending stiffness, T is cable tension, and KR is rotational stiffness. L here is a cable length. Equation of motion, a solution and most shapes equations can be seen from equation 6 to equation 8. By discretize the most shape equation into the matrix form, the cable eigenfrequency can be determined if we know the stiffness matrix and mass matrix. So in this study, the finite difference method is applied to derive the stiffness matrix and mass matrix. A finite difference method is quite familiar with some of you. The principle is it will replace derivatives in differential equation by finite difference approximation. For example, here is the first derivative of the differential equation, and this will be replaced by finite difference approximation like this. So by using the finite difference methods, as I already mentioned, we can determine mass matrix and stiffness matrix as presented in equation 14 and 15. So each row of these matrices represent for one node of these cable models. After having cable properties, after having cable properties and after having stiffness matrix, mass matrix, we can determine the eigenfrequency. Eigenfrequency here means natural frequency of the cable. So this slide, I'm going to talk about the procedures for estimation of cable tension using ANNs. There are three main steps. The first step, we will generate the data sets for training based on the design parameters of the cables. Here is rotational restraints will be generated from nearly hinge end to nearly fixed end. So having these parameters, we can compute the natural frequency of the cables. After having these data sets, we will use for training, validation, and testing in ANNs with the inputs parameters here and outputs is the cable tension. So after step number 2, we will get the well-trained models, and this well-trained model will be used to estimate cable tension. The inputs for this trained model is a measure cable frequency, length, and mass per unit length. The outputs after training, after this model, the output we can get here is a cable tension. The methodology developed in this study is used to identify 6 cable tension in 6 selected cable in one existing bridge in Vietnam, including 3 steps, as I already mentioned: generating datasets, training datasets, and then estimation cable tension from trained model. So I'm showing here these figures show the correlation between predicted values and target values with very high correlations, including training, validation, and testing. So after having this model with the well-trained, we can use for estimation of cable tension of 6 selected cables from the measure frequency, cable length, and weight per unit length. In here, we consider cable bending stiffness and rotational restraints, I mean boundary conditions as unknown parameters, but we can still get the cable tension. So by looking at this figure, we can say that blue one is cable tension for the fixed end, and gray one is cable tension for hinge end. And orange one is the value of cable tension with unknown bending stiffness and unknown boundary conditions, and they show a very good results of cable estimations. So here is conclusions. The important is we can estimate cable tension without knowing cable bending stiffness and boundary condition by using the application of SHM&ES. Okay, thank you for listening.
Now, thank
Yes.
you for your interesting presentation, Dr. Lê Xuân Lưu. Now, we have some question. Some question, please. I would like to invite some
Question, please. Yeah. So thank you for nice presentation.
Yes.
I want just to know about your application using artificial neural networks.
Yes.
What about for the number of collected data?
Yes.
So inputs, outputs, and the number of collected data also can affect the results or no? Can you please?
Yes, so thank you for your question. So your question may be regarding the numbers of the corrected data. So in this study, our purpose is to identify cable tensions, and we use the cable properties and the measure frequency as inputs for the training. So here we can see I'm showing this one. Actually, yes, of course, it has the, if we have like for example a frequency, we use the measure frequency, and in this study I use the fundamental measure frequency. Just mean it's one frequency. And your question may be like if we have more frequencies, a higher vibration mode, we can like improve the accuracy of predictions. However, we can observe from this study that we have here only one the measure frequency, but with the simple techniques from the.
So you mean only the first mode or what?
Yes. So let me point out this. We used here in this study only first mode vibration, but I can say that if we have higher vibration mode, we can. Yeah, of course, cable tension is constant. The static. The core tension is constant. It means that for the first mode we can predict cable tensions. For higher modes we can predict cable tensions, and those values should be the same. But in this study we don't have the higher vibration mode, because when we excite the cables, like release, pull and release, we like a man-made powers, we can just measure first vibration mode, and that's the reason why in this study I used only the first mode of vibration.
Okay.
Yes.
Okay. Now, I have a small question for you.
Yes, please.
Can you explain the figure number 10 to compare the tension gap in tension cable in, yes.
This one, right? Yes.
Comparison of between fixed hinge and rotation
Yes.
can is
Yes.
cable.
Yes. Thank you, Professor Nguyễn Trọng Phúc, for your questions. So let me explain a little bit here about these figures. So in my study, I focus on unknown bending stiffness and unknown boundary conditions. So as we know that the boundary condition as cable end is unknown, because we cannot say for sure that is a fixed end or hinge ends. However, fixed end boundary conditions and hinge end boundary condition are two conventional cases. And therefore, in this one, for 6 selected cables, for example, cable 6, this one here, the hinge fixed end, we compute from the analytical solution, and hinge end we compute from the analytical solution. And rotational restraints, and here is in my study unknowns, and we use the application of artificial networks and treated boundary condition as unknown. We don't know what kind of boundary conditions. We don't know the rotational stiffness, but we in activists before trainings, but during training we generate the boundary condition from the fixed end to hinge end, and therefore we can say that even we don't know boundary conditions, but we can cover the whole range of the stiffness from the 0, it means hinge end, and infinity, it means fixed ends. And this figure, the orange columns show the values of rotational values of cable tensions for rotational restraint with unknown values of stiffness. And
these values stays at the between, it means within the range from the hinge end to the fixed end values. So that is my explanation for this figure.
Yeah, I see. Now, that is the end of this presentation.
Okay, thank you for.
The audience have more questions. Please contact to presenter. Now, the next presentation of I would like to Dr. Le Xuân Lưu in next presentation. Dr. Le Xuân Lưu, are you ready?
So actually, yes,
The
I'm ready, but I
in 44, number 44, effect of static wind loss on reduction of damping in the cable stay with a damper.
Yes, let me share again.
Yes, okay, please. Good morning, everybody. My name is Le Xuân Lưu. I come from Vietnam and from University of Transport and Communications. So today I want to share my study with the title, Effects of Static Wind Loss on Reduction of Damping in Stay Cable with a Damper. So the content includes 5 sections from introduction to conclusions. And here is introduction. As you may know that cable is one of the important elements in cable supported bridge. However, inherent damping in cable is small, and therefore the dampers are often installed to cable to suppress, mitigate, or even eliminate unwanted vibrations of cables. For example, rain wind induced vibration or vortex induced vibrations. So the problem is the actual effectiveness of damper is small, and some researchers in this field, they commented that a damper effectiveness is on the order of 50 to 70% of that in theory. So far, there are 5 factors regarding reduction of cable damping. For example, damper stiffness, damper support stiffness like this, cable sag, or cable bending stiffness, or effects of rotational restraints between a cable and a damper. So in this study, we focus on the effects of static wind load on dynamic characteristics of cable, including frequency, mode shape, and the model damping. The methodology here is model analysis and the finite difference method. So I would like to show here a schematic diagram of the cable. We show here the cable at the static state and the cable in dynamic state. In static state, cable is subjected to dead load, and in dynamic state, cable is subjected to dynamic load. Cable is installed with a viscous damper at damper location A, and C is a viscous coefficient. KD here is damper stiffness. Boundary conditions at cable end are rotational restraint ends. And in our study, the dead loads includes static wind load, the first component here, and cable self weight. In these figures, we show the cable element addressed, I mean, in a static state and in vibration. By taking, equilibrium of these elements, we can derive equation of motion like equation 2 and solution in terms of harmonic form like this. And after substitution of equation 3 into equation of motion, we can get the mode shape equation here. EI here is bending stiffness, T here is cable tension, delta T is an additional cable tension during vibration, C means damper coefficient, and M here is mass per unit length. So we will use the finite difference method to discretize the mode shape equations into harmonic form like this. in terms of stiffness matrix and damping matrix and mass matrix. So the finite difference methods is that the principle is we will replace the derivatives of the component in the differential equation by a finite difference approximation. For example, the first derivative like this, and it can be replaced by a finite difference quantity like this. So after having stiffness matrix, damping matrix, and mass matrix, and solving this equation with some mathematical manipulation here, we can determine parameter P, and then we can calculate frequency and damping ratio. Damping ratio is a real product of complex number P. So I would like to show some results. The first one is effects of cable bending stiffness on cable sag and cable damping. So in 2000, Tabatai and Mirabi, they proposed the solution of cable damping of cable with a viscous damper, and they consider cable sag. But in their study, cable sag is a simple formulation without consideration of bending stiffness. In this study, we consider bending stiffness. And for small bending stiffness, we can say that our study and study of Tabatabai have very small difference, and they may have the same effects on the cable damping with the error less than 1%. However, for large bending stiffness, we can say that there is a significant difference in terms of configuration of cable sag with bending stiffness here and without bending stiffness. So therefore, for the large bending stiffness cable and the cable and damper location at the cable end, close to cable end, for example, 2% or 5% of cable length, we can see that cable sag without bending stiffness will trigger overestimation of cable damping from 2% to the 6%. So I'm showing the next result. I want to talk about the effects of static wind loads on the cable frequency and reduction of attainable damping. This axis show the attainable damping contributed by viscous damper, and this axis show the different values of wind speed. And we can say that in the presence of wind speed or increased wind speed acting on the cable damping will decrease. And on the other hand, the cable natural frequency will increase. I'm showing some figures here with different body condition, hinge and body condition, fixed and body condition, and different rotational restraint and condition for damping and for natural frequency. We can also see here the different configuration of cable sag with different values of mean wind speed for the fixed end cables and hinge and cable. Here is conclusions. The most important here is we pointed out that in the presence of static wind load on the cable, cable damping will decrease and the cable frequency will increase. Okay, thank you for listening.
Okay, thank you for your interesting presentation, Lesson Lu, with special topics.
Yes.
Okay. Professor Yu Hong Thẩm have a question for you.
Yes, please.
My name is Thẩm.
Yes.
I thank you for your interesting presentation. I have a
Yes.
question for you.
Yes.
About the boundary condition when you use the finite difference method in order to analyze.
Yes.
What treatment about the beginning of the value when you have the backward algorithm, for example? Understand what I mean? Because you want to calculate any displacement. For example, we have the backward and forward. So at the beginning point. Have you any treatment for about that? Thank you very much.
Yes, thank you so much for your questions. It seems that you're pretty and really familiar with the finite difference methods. So regarding your questions, in this study, the finite difference scheme I use here is a central scheme. And as you pointed out, that the beginning point is very important, because at the beginning point, we need the information of previous point and the information of one step of the dash node. So in this point, I used, for example, we divided the cable into the internal node, and for the fourth node, the information of previous node, for example, the nodes -1, and then the nodes 0, and then the nodes 1. At the nodes 0, I will have to use the information of nodes -1, and we use the boundary condition. Here is the bending moment and the shear force for the boundary condition to know the information of the nodes -1. So that is how I treat the.
Okay. I am sorry. I just want to ask about the mathematical expression or mathematical condition for it, not a physical or mechanical condition, because you use the boundary condition. That's definitely right, but I think that about the algorithm or some technique or mathematical expression there. You understand what I mean?
Yes, I understand. And you mean like to write the differential, the finite difference method for the first node. You mean that we have to know the information of the previous node, for example, nodes -1, right? Yes, and here, so if you have time, I can show you the equations, the mathematical equations. So how about that? I will explain through that formulation.
Yeah.
Okay.
Okay.
Okay. So yes, I'm going to show.
The next question. Next question, please. Okay. I have a very small question for you.
Yes.
Can you
please.
explain the effect of static wind loss? Static wind loss on dynamic characteristics in this aim of this study. I think the static wind loss on dynamic characteristics.
Yes. So thank you so much, Dr. Professor Wendell Fu, for your question. So in my study, so we consider, as we know, that the wind will include two components. That is the mean wind values and the fluctuation components. So in my study, I consider the mean values at the dead load, and this as extra. We have the cable, we have dead loads by cell weight, and we have if the existence of mean wind values acting on the cables, and it will reduce, or it will impact on the effectiveness of damper system. And we treat the mean values of wind speed here with the drag coefficient, air density, and when we compute the static wind load, and we the cable will subject us to get the static wind load and dead load and shell width, and at that time we will determine again the damping, the modal dampings, and we pointed out that the modal damping is lower than the theory values. Theory value here is mean no consider of the static wind load, and static wind load here is just one case of a damping reduction in this study.
Okay.
Yes. So
for me.
Actually, about the formulation. Okay. So
in this slide, I see effective dead loss, ice loss.
Yes. So
that's on reduction of carbonamine.
yes.
Can you explain? I know the globin phenomenon depend on ice loss in the carbon.
Yes. So thank you for the Professor Nguyễn Trọng Phước, but I'm really sorry about your question, but I would get back to the question of maybe your colleagues next to you about the mathematical formulation to how to determine the information of the footnote. Professors, let me introduce like this. For example, if we want to, I will write the finite difference of scheme from the node number 1 to node n, and for node number 1 we need the information from node 0 and the nodes before that one, because we have derivative, the fourth derivative we have a second orders, and here is I write for node number 1. We don't know the information of for example, displacement of the node minus 1, node minus 1, it means it's right. So, and then so we apply the boundary conditions. For example, here is a boundary condition regarding the bending moment, and then we have definitely get the information of nodes minus 1, and then we compute the next node, nodes 1 and node 0. That is my explanation.
Thank you, presenter. That is the end of this presentation.
Hi, thank you so much.
The next presentation, I would like to also up paper number 30, title of application of artificial neural network for recovering GPS RTK data in the monitoring of cable hybrid information. With Nguyễn Thị Linh and Nguyễn Hữu Hưng. Nguyễn Thị Linh and Nguyễn Hữu Hưng. So I be not here. Nguyễn Thị Linh and Nguyễn Hữu Hưng. No. Not yet. I think that Nguyễn Thị Linh and Nguyễn Hữu Hưng is not online in here. Now, this session is moved to the next presentation, number 23, multi-layer perception neural network for damage identification based on dynamic analysis, with the group author, many authors of this presentation: Ramazan Ali Zafari, please. Okay. I would like to invite Mr. Ramazan Ali Zafari.
Yes, I think it's here. Ramazan Ali Jafari is here. Can you just give a moment to him to join? Yes, Ali, can you hear us or?
No, I saw in this room Mr. Zakat.
Can you, Professor, ask for another presentation, please? And then we can go back to Professor Ali Jafari.
Because we also against referee is here.
Yeah, he's here. Yeah, he's here. Yeah.
Can he start now?
I don't know if he can hear us or no. Can you go to the next presentation and then we can ask Ali to go back?
Yeah, because
we finished the section or?
Yeah, no one here. Only Ramazan Ali.
So the last one?
Yeah, the last one already is presented.
Already present. Yeah. Okay. Okay. Yeah. Okay. Okay.
And now,
Can we wait a moment, please? Let's just talk. Let me text him again.
Okay.
Where is Ali? Ali.
We are waiting 1 minute. Mr. Ramadan is connecting.
Please, Ali, can you hear us or I don't know. Còn các sinh viên còn nghe không đề cập đến chuyện truyền thông đó. Ali, can you unmute your microphone, please? Please unmute your microphone. No. Try to unmute your microphone because still turn off. Or can you share your presentation first, then we can confirm that.
Okay, you play this presentation.
Samir, so he
Yes.
wants to share the screen. I think he had problem.
Yeah, I asked him to share the screen, but I don't know.
But he can hear us and see the sections. Yes, I think he have problem in share screen.
At least he has to unmute the microphone to hear you.
Họ dùng không quen. Thì bắt đầu em có dùng cái trò chim để họ quen chim hơn. Việt Nam mình dùng thôi cái chỗ đó được hết rồi thì nói cho được nếu thì hỏi nó được qua cái gì đó anh Tuấn nha.
Okay. I'm sorry, Mr. Ramazan. In the next presentation, I would like to return the presentation number 424. Nguyễn Anh Tuấn, Mr. Nguyễn Anh Tuấn, Mr. Nguyễn Anh Tuấn, please.
Yes.
Please, Mr. Shar, what is the name of which title that you ask now?
The title of the paper of Nguyễn Anh Tuấn is optimization process parameter.
Okay, good. Okay,
yeah.
Okay, thank you. Thank you. You can go ahead. Okay. Yeah.
Yeah, okay. We saw this presentation.
First of all, I would like to introduce about semi-solid processing.
Sorry, Con, can you ask him to record the video if he has, because we can't hear him? Or...
Yeah, we have problem in pre-recording.
Yes, can you ask
now you
him
can
to
show,
record the video? Or
yeah, you only see the video, that's all. With no sound is okay.
Bye bye thầy Thắm. Have a nice day. Rất là Thắm.
Can you ask the presenter?
Just why we because Dr. Tinh Anh finished and we ask one or two questions. That's all.
Okay. Thank you for video your presentation, Mr. Nguyễn Tuấn Anh.
Yes, thank you for consider my presentation.
Right. Any question? Question, please. Okay. That is the end of this session. We have three session in presentation. Three presentation. Sorry. Three presentation including 24, 43, and 44. And number of this absent in our presentation number 81 and number 30. Okay, that is the end of this session. Now, in the next time we have a break, approximate 15 minutes. That this table time is continue to 12 and 14, 12 and 12 third, 12 and 12 13. I'm sorry, 12 and 13. With the section one, with chair Professor Dr. Erika Maganini. Okay. Now that is the end of this session. We would like to invite everybody to hear from the trail 30. Trail 30. Yeah.
Yes, thank you, Professor Nguyễn Trọng Phước, for him to already finish the chair of the sections one. And now the time for break time. Thereafter, we will start with the section, the continue this section will be chaired by Professor Erika Magani from Italy. Yes, and see you again on 12:30 p.m. Yes, thank you. See you.
sorry. Sorry. Someone here or? I think, Erika, can you start now? Yes, we can't hear you. Can you turn on your microphone, please? Okay. We can't hear you, Erika. Turn on your microphone. Turn on your microphone. Not too much. I think. Yes. Can you speak, please? Yes. Okay, Erika. Yes. Can you start now?
From Polytechnic University of Marke, and I'm the chair of the second part of the session about optimization and machine learning for engineering structure. Let's start with the second part of the session. The first presentation is characteristic of semi-rigid steel frames with fuzzy variables. The speaker is Vietung Chong. He is the author here. The author is here.
I don't know. Maybe can we wait a moment, please? If,
Okay, we can wait a minute and then we can. clear. So we can move on with the next presentation. The next presentation is of the same author, so I can move on. Next presentation is a chip optimization algorithm for vibration-based damage detection of damaged steel truss. The speaker is Tamir Tashusha. The author isn't here, so I will share with you the presentation.
But Erika, we can't hear. We can't hear the slide.
Okay, one moment.
Can you repeat, please?
Okay, I restart the presentation. Okay.
No, we can't hear Erika. Let me share by myself. Please.
Okay, thank you.
Oh, okay. Moment, please.
Yes. Take your time, no problem.
Because it was in meet, so. Okay. And now? Thanks, Mr. Sheriff. So, good afternoon, everybody.
We can see the presentation. We can't.
You can't see my presentation?
Yes, we can't. We hear the speaker, but we can't see the presentation.
Oh, because I already shared, but I don't know what's the problem. Let me just see. Share.
Jimmy, you cannot share your presentation.
Yes, I already share. I don't know what happened for new share. Okay, no, I feel that's it. Let me just stop sharing and. So, and now, still not.
Still not.
No.
No.
Can you try again, Erika, or can you hear?
Okay. I can try again. Let me know. Okay, one moment, sorry.
So, any problem?
Erika, can you stop, please? I will try to record the video. Can you stop, please?
Okay.
You click on record or share screen or what?
I click on start with the presentation, but I don't click record anything.
Okay, let me try with the...
If you do Harry
give you the permission.
Can
Can someone give me the permission to record my video or?
No, you just can just share your video. That's all.
Yes, but they asked to get the permission from you. What happened?
Yêu cần được cho phép cái xe cái video là sao? Cái convoy đúng không? Mà nhưng mà nó lại là có yêu cầu máy chủ cho có vấn đề gì?
Erika, can you see my screen or no?
Not, I can see your screen. Not, no. I see just your name on the screen.
Okay. I don't know what. Can you try again, please? Can you try again, please?
Presentation.
Yes.
Okay.
But without Erika, without sharing, can you hear the presentation or no?
In my PC, I can hear the presentation, but I don't know if you can hear the presentation. Can you hear the presentation?
No, I can't. I don't know what happened. Can you try again? Okay, try again and then we'll see.
Okay, okay. One moment.
Hi guys, I think I got this problem before. So can you just use one computer and then your phone as well? You talk to the phone and you use the screen to share your presentation. So everyone can hear your talk and can see your screen as well.
Okay, I can start with the presentation. I try.
Okay, Erika. I can't hear you. Okay, you can start the video. I will try to present by myself. Start only the video.
You can present by myself. That's all.
Yeah, I will present by myself. Okay, no problem.
Yes, present by myself.
Yeah. Okay. Okay, you can start the video, please.
Okay, sorry, I don't understand. Okay, now I will. Okay, one moment. Sorry.
Just present by yourself. That's all.
Okay, so thanks, Mr. Chair. So good afternoon, everybody. So today I would like to present a shame optimization algorithm for vibration-based damage detection of damaged steel truss structure. So for the work plan of my presentation, I will try to to explain the important things for structural health monitoring and how to use optimization techniques as an inverse problem. So in this case, we use a shame optimization algorithm, and we use a truss structure using finite element method, and two different kinds of structures are investigated to study the effectiveness of this algorithm. Okay, next slide, please. Next slide, Erika, please. Okay, so the structural health monitoring, it's quite an important issue for the engineering applications. So in this way, we have to create a new application or new technique to solve the exact location of damaged elements. So this is the important things. So the content of my work based on different stage, I will try to summarize everything here. So first, the damage identification method in 10 and 25 bar plan truss structure based on the inverse problem. The both structure are built in MATLAB using MATLAB software using finite element method. A new optimization technique investigated recently, namely shape optimization algorithm created recently also, is involved for damage identification. The objective function is based on measured and calculated frequency and the mode shape to analyze the conversion study of the fitness and damaged elements. So model assurance criteria is used to represent the mode shape into the objective function as well as frequency. So we have compared two objective function, the first one based on the mode shape and the second one based on the frequency. And we can see that the provided results are more accurate using this algorithm. Next slide, please. I can't. Okay, so the inverse problem. I will try to explain what is the inverse problem to solve the damage identification problem. So for this algorithm, we have some parameters can be selected, like the number of population and the number of population size and number of generation, and the objective function try to compare between measured and calculated from the numerical analysis or the experimental analysis, and then compare with the computer using this algorithm. So for each generation, we have to compare the frequency or the exact frequency and the exact mode shape with the computer for each generation to converge to be converged to the damaged element. So next slide, I don't know. So in our study, we have considered two kind of structure. The first one is 10 bar planar truss structure, and the second one is more complex than the first one, is 25 planar bar structure. So the mechanical and geometrical properties of both structures are investigated in this slide. So two cases are investigated for each structure based on single and multiple damage. So for the case number one, we have damaged element number 6 by reduction in stiffness 20%, and case 2, 4 and 5 elements for using 25 and 35 reduction in stiffness. And for the second structure, the single damaged element is 4 with reduction in stiffness 20%. And for multiple damage, we have 19 and 24 using 25 and 35 reduction in stiffness respectively. So the objective function used here, so we have to compare between frequency measured and calculated, as mentioned in the objective function number 1, and the second objective function compare Mach value between measured and calculated, and the Mach value based on the mode shape. Next slide, please. So in this slide, we summarize the results between actual and the predicted results for the first objective function and the second objective function of the first structure, 10 planar bar truss structure. And we can see that the provided results are more accurate for the single damage, for frequency, and for the mode shape. And we can see that the CPU time, it's very less for the frequency compared with a mode shape as presented in the table. So for in here, I present the multiple damage, and we can see that the provided results is more accurate for the frequency compared with the mode shape. So we can see that the conversion study for the frequency after only few iteration compared with the objective function number 2. And we can see that the provided results can be detected after 35 iteration. And the conversion study of the major element also presented. So now I go to the second structure, 25 planar bar structure, and we can see that the provided results also here for the complex structure using both objective function. And we can see that the provided results can be detected only after few iterations using a frequency and mode shape, and also for the CPU time, we can see are very close for both objective function. Okay, now in this slide, also I present the multiple damage for 25 bar planar structure, and we can see that the provided results for frequency can be detected only after 4 iteration compared with a mode shape after 55 iteration. And we can see that this algorithm can predict correctly the damaged element for both structure. So this study provided the damage identification in 10 and 25 bar plan truss structure based on the inverse problem using shim optimization, and MATLAB software using find element method is used to build the structure. Single and multiple damage cases with different level are investigated to study the effectiveness of shim optimization, and the objective function based on the mode shape and the frequency are used to compare between measured and calculated. And we can see that this algorithm provides good results after only few iterations. So thank you for your listening.
Okay.
Okay. Yes, yes.
Any questions?
I have a small question for Dr. Samir.
Yeah.
About the data, how did you choose, or how did you select the data? Damping is 20% of damping, and about the percentage of damage in 25 or 35 percentage of damage. Why? Thank you.
So what do you mean by the data, please? Because in this example, I didn't use the data. So the optimization techniques can predict randomly the damaged elements and the level of damage. And during the conversion study, we have to predict which damaged element and which damaged level.
I mean that because in the slide D7, please.
I will try to check.
I can share again the
presentation. D7. Okay, no problem. Okay, no problem. Okay, so we have the damage. For example, we have the damaged element 6 with reduction in stiffness 20. So what do you mean by this?
Okay, about how did you, why did you choose the percentage of damage is 25 and 35%, and how did you select the data? Why? The reason about the damping 20%.
No, for us, we only select randomly. We only select randomly reduction in stiffness, and then we have to look for this. You can select what you want. You can select less reduction in stiffness or high reduction in stiffness. So depend on us or on you. Yes.
Okay. Are there any questions? Okay.
Hello, and now Mr. Huang, a member of Faculty of Civil Engineering, Ho Chi Minh City Open University, will ask one question. Thank you, Dr. Samir, for your present. I have two questions. The first question is, how many number MOSFET and how many number frequency did you use to establish the objective function? And
so as you, okay, thank you very much. So for the frequency, I used the first three mod. Okay.
Three mods.
Yeah, three mods. Yeah, three mods. And for the mod shape, we use the Mach value. So Mach value can be calculated based on the number of mods selected. So the mod selected for Mach value also 3. So we have matrix 3 by 3.
Three
Yeah.
You do three frequency and three MOSFET for establishing.
Yes. Yes. Yeah. Exactly. Yes.
Okay. And the second question, your algorithm use, I see the conversion rate is very fast, and I don't see the fluctuation. So the algorithm have an advantage, right? Can you explain?
Yeah, of course. Yeah, has advantage.
Can you explain what is advantage in this your algorithm that you use to your research?
Yes, the advantage of this algorithm, so after the provided results, we can see that the results can be found only after few iterations for the frequency. Maybe we can compare also with some benchmark example, and we can make sure that this algorithm has a good convergence compared with the other algorithm, because I have already did some applications and I can find the results, for example, only after 10 iteration, but for this algorithm, I have detected that this algorithm can be found the results only after 3 iteration. So this is the advantage of this algorithm. Also for the CPU time, it's better than the others, because you see that conference paper, so I didn't put everything, or I didn't compare also with other techniques, but I make sure that this algorithm it's better. And also it's published only recently, so we investigate this algorithm for damage identification problem.
How about the time cost of the computer when compared with the other algorithms? How about the cost?
The time. You can see in my slides that that the CPU time it's around. Let me just see the table. Around 200 seconds. So for other algorithms, so more than 250 seconds. Okay, so this is for 10 bar Planck structure, and for the second structure, we can see that 714, and for other optimization techniques, more than 800. Okay.
Thank you.
Okay. Yeah.
Other questions? Okay. Thank you, Dr. Kadir, for your interesting presentation. I think that we can move on with the next presentation. The next presentation is model updating of frame structure using equilibrium optimizer and triple search algorithms. The speaker is Samir Tashisha, but
We'll try to present also.
So I can share the presentation.
Okay, you can share now. Okay.
Okay.
can you repeat, please, Erika? Can you start again, please?
Okay, sorry. I can start again.
Sorry for the confusing.
No problem.
Okay, so now I will try to present for this presentation model updating of frame structure using equilibrium optimizer and the cuckoo search algorithm. So the work plan of this presentation. So I will try to explain the inverse problem using cuckoo search algorithm and equilibrium optimizer algorithm. And I will try to calibrate the healthy structure and the measure structure based on experimental model analysis, and finally some conclusion and remarks. So the structural health monitoring is a quite important issue for engineering applications, and we can see that this topic, it's a very interesting now, but our objective that we have to solve this problem very fast, cheaper, and accurately. So the content of this presentation, so this work presents a conversion study and the CPU time, because the CPU time is interesting to solve the problem between two optimization techniques. The first one is equilibrium optimizer and cuckoo search. Both optimization techniques use it as an inverse problem to calibrate a finite element model of frame structure based on measurement. Different generation and the population to test the accuracy of the optimization techniques are provided for healthy and damaged frame structure. So the investigated results show that the equilibrium optimizer has a good convergence with less CPU time compared with the cuckoo search algorithm. So to study the effectiveness of both algorithms, the inverse problem is investigated to study both algorithms, and the objective function used here for this application based on the frequency, because for the measurement we have collected only the frequency. So both algorithm can detect the new stiffness matrix, because in here we use a model reduction. So the model reduction of this structure, we use a new stiffness matrix, and this stiffness matrix can be found by both optimization techniques. And for the objective function, we have to compare the frequency by measured and calculated. So for this application, so we can see that the four-story shear steel frame and the mechanical and the geometrical properties are investigated in the top of this slide, and we have the reduction in stiffness in the story number 3. So for this structure, we have healthy and damaged structure, but for the optimization techniques, we study the effectiveness of both based on. So the first one, we fixed the number of iteration and by modify the number of population size. And the second stage, we fixed the number of population size and by modify the number of iterations, so 50, 100, and 500. And now, the results provided here, it's for healthy frame structure. So in this table, I summarized all the results provided by both algorithms. We can see that the initial frequency from finite element method, and for the experimental results and how to calibrate this frequency. So as mentioned before, the number of iteration here is fixed. So it's 50 iterations, and the number of population size are modified. And we can see that the provided results are more accurate for equilibrium optimizer using 500 population. Furthermore, cuckoo search has to provide 1000 population size. And you can see also that the CPU time for equilibrium optimizer has less CPU time compared with the cuckoo search algorithm. So these applications for 50 iteration, and by modify the number of population size. And the next analysis. So in this slide, I have presented the conversion study for both optimization techniques for all the cases. And in here, we can see that the provided results for equilibrium optimizer, the red color, has good conversions compared with the cuckoo search using 100 population, 500,000 and 2,000 population size. So, and now for the healthy structure, so the second stage, we fixed the number of population or the number of population, and by modify the number of iteration as mentioned in this table. And we can see also that the provided results are more accurate for equilibrium optimizer when we use 100 iteration. You can see that the equilibrium optimizer has the same frequency compared with the experimental measurement. Furthermore, for the cuckoo search, we have to select 500 iteration to get more accurate results or to more accurate frequency compared with the measurement. Now, I summarize in here also the conversion study of both algorithm, and we can say that equilibrium optimizer also has a good results after modify the number of generation and keeping the same number of population size for 3 cases. Okay, now for the damaged frame structure. So in here we use the model reduction. We created a new matrix or new stiffness matrix can be provided by both optimization techniques. So in the first stage, the number of iteration is fixed, is 50 iteration, and by modify the number of population size, 100, 500, 1,000, and 2,000. And we can see that the provided results is more accurate also for equilibrium optimizer in the damaged structure using 500 population. And this slide summarizes the conversion study of each case, and we can see that the provided results are more accurate for equilibrium optimizer. We can see that the conversion study can be detected only after few iterations compared with the cuckoo search algorithm after modify the number of population. But for this stage, also the number of population size is fixed, is 200, and the number of iteration are modified. We use 50, 100, and 50 iteration. So we can see that the provided results are more accurate using 100 iteration compared with the cuckoo search 500 iteration. So also for the CPU time has less CPU time compared with the cuckoo search algorithm. And also in this slide, I summarized the conversion study for each cases. And we can see that the provided results can be found after only few iterations compared with the cuckoo search. Okay. Now, I will try to summarize all the advantage of this paper, of this present study, and we can see that the conversion study of cuckoo search and equilibrium based on model updating and damage identification in frame structure and the inverse problem is investigated to study the effectiveness of both algorithm and the objective function compared, measured and calculated frequency using both algorithm, cuckoo search and equilibrium optimizer, and the provided results show that the equilibrium optimizer has a good convergence, less CPU time compared with the cuckoo search algorithm. So thank you for your attention.
Okay. Are there any questions? Any
Yes,
questions?
Kong, do you have question, Kong?
Yes, no question. And no question for.
I think, Erika, you can go to the next presentation.
Okay.
Okay, thank you. Thank you very much.
For your interesting presentation. We can move on with the next presentation. The title is Comparison of Swarm Intelligence Algorithms for Optimization Problems. The speaker is Min Ongli.
Okay. Today I will introduce dạ biết rồi. Hello. Okay. Today I will present the comparison of swarm intelligence algorithm for optimization problem. I choose 4 optimization algorithm to compare. The first one I choose the party swarm optimization, namely PSO. The second I choose the artificial bee colony, ABC. And the second I choose the cuckoo search. And the final I choose the choreograph optimizer. The present have a 6 section. The first section I will introduce fast the search strategy of each algorithm. The PSO algorithm just the search strategy using the update velocity, and the main idea of the PSO is use the local optimize and global optimize. After each iteration, the new position have a 10 near local best or global best to the balance two significant feature is the exploitation and exploration. The second is the ABC. The algorithm ABC is 3 phase. The first phase is employee behavior phase. The employee behavior phase is the employee behavior phase. The employee behavior phase is the search the hive with a quantity nesting, record information and say on the locker beer and Scott beer. The unlocker beers based on the information from the employee beer, the locker beer will develop a new position to expand the search space. And if the new position is not good, the Scott beer will record the information and send to the Scott beer. So Scott beer phase is the must decision. If the food is best, the Scott beer will replace by a new food. This is the search strategy of the artificial bee colony. And the second is cuckoo search. The search strategy in cuckoo search using the Levy fly. The Levy fly is the random walk whose step length orbit the Levy distribution. So the cuckoo search use the host nest as at the cuckoo burst select the host nest to the lay the egg. So if the eggs if the and comparison the nest will finish better if the egg of cuckoo search is better, the nest will keep and use to the next iteration. But if the finish is worse, the nest will be abandoned and rebuild with a new nest.
This is the search strategy in the cookie search, and the search strategy in the rate growth optimization use the first, the second, and the three of the finished value as a agenda. So if the 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 value is smaller than 0, the ability of exploitation. But if the value of the first of the three finished bandit, the free value of the bandit is the larger 0, the ability of the exploration in the graph. So to demonstrate the influence and the effectiveness of S algorithm, we use 10 functions in the bandmask to the comparison for the conversion rate. As you see, for the first function, almost I record the cookie search either have the best performance than all the algorithm. And the second is the worst optimization. And the best worst and the worst optimization is the PSO. Cookie search also very conversion in very fast, while PSO very slow. That because the velocity updating process in PSO is not enough long to expand the new search space. And this is the movement strategy in S algorithm. You can see the cookie search and the web optimization always expand the exploration to the search global optimize, while PSO and ABC seem stuck at the local optimize. So the performance of the web and the cookie search, it have the best performance, a better performance than the PSO and the ABC, especially in function 7. Also, web algorithm have the conversion faster, but the accuracy level of cookie search is still better. This is the statistic of the comparison. The best finish, mean best, and standard deviation of the H function using PSO, ABC, cookie search, and web. I can summarize like that. The cookie search is also give the best performance on smart the function, except the function 4. The function 4, the ABC is the best. The ABC, the best is function 4, function 5, and function 6. And the cookie search is on smart register the best performance on the algorithm. And can calculation like that. The cookie search is the best performance in comparison with the other algorithm. The PSO is the worst performance in 3 algorithm. ABC algorithm recognize an instability in some kind particular problem. Both optimization is potential algorithm. The best value is registered in the web optimization seem only behind the cookie search. And thank you. Your within myself.
Okay, thank you for your presentation. Are there any questions?
Samir, can you ask one question?
Yes, I don't know why you didn't consider the CPU time to make a comparison, because for me the CPU time is interesting.
I just compare the result performance of the 5 global optimize and expand the search space. I don't compare about the cost time of the CPU. I will If I have time, I will ask more.
Yes, yes, yes. So should be, I think, compared because the CPU time it's interesting. We can only, for example, increase the number of population size and get good results compared with the other with the same. Same.
Okay.
I mean, yes. Can you understand what I mean, or?
On the algorithm have the same initial condition, same the number
Yes,
size.
the initial condition, but you see, sometimes we cannot find the good results for the faster optimization technique. So in this way, we can increase a little bit the number of population size, and for example, can find the good results with less CPU time compared with the other. So this is what also I mentioned this to Professor Rao this morning. And
yes, I think that's a good idea for me. I just compare.
So from now, try to include another part. So CPU time.
Yes. Okay. Thank you for your advice. I will.
Okay. Okay.
Yes.
Okay.
Thank you, Dr. Ming for your interesting presentation. So we can move on with the next presentation. The title is Genetic and Particles for Optimization Algorithms for Damage Detection of Beam-like Structures using Residual Force Method. The speaker is Dr. Romzina Luz Jafri Talakulu.
I think he has a technical problem. This professor, I mentioned already this morning, but I don't know.
Can you repeat the question?
No. Now we move to the next presentation. Now we finish. You. Okay, good. I think now. Okay, Erika, maybe now we have to wait a little bit and then go.
No, next is the Mustafa. Okay.
Yes, so we have to wait until 45. Okay, now we have break, I think. Erika. So
okay. We can have a break.
It is guys online.
So this guy, he found he has a technical problem, so I don't know. He cannot.
So can he's
he cannot join the. I don't know. He mentioned that we'll send the video, but still waiting. I don't know if.
Yeah, if he cannot, we can move, take a break because
Yes,
now
I
it's
think we
now
have to
1:30.
Yeah.
See me?
Yes. I think now we have to take a break.
Yeah, take a break. Thereafter, we'll move to the paper 1000 from Osla Brahim.
Yes, he's here. He's here.
Is he here?
Yeah, he's here.
Yeah. Okay. Now I think we can take a break for 15 minutes.
Okay. Yes.
Okay.
Okay. Now we take a break for 15 minutes. Thereafter, we will continue with the paper 1000. Experimental and numerical investigations of the North Pole interaction in tensile net specimens of API X70 steel. Okay. Okay, 15 minutes for practice.
Hi.
Yes, Erika, can you start the show? Can you continue? Or?
Okay. You can continue.
Okay, you can start. Okay.
The next presentation is experimental and numerical investigation of the non-shoal interaction in tensile test specimen of API X70C. The speaker is Hulad Brahim. Okay, you can start with the presentation. Thank you.
Thank you. Hi everyone. I think I have a problem in my microphone, so I prefer to start my video direct. Excuse me. Hi, hello everyone. My name is Mumin. I am a mechanical engineering and PhD student. Thank you all for accepting my presentation. Today I am going to talk about experimental and numerical investigators of non-shoal interaction in tonsil test specimen of APA X70 steel. So the outline of this work. First, I am going to give a short introduction of pilot of this study. So the presence of the holes and more generally of notch and other connection gaps leads to the weakening of structure due to local upper stresses called stress concentration. For example, in this figure, the pipeline onshore and offshore. Can you see the problem in the aircraft? So when the presence of stress concentration is inevitable, it's necessary to know the stress concentration factor associated with each geometry. A notion introduced in this problem and in order to the dimension the structure, large size hole lead to the strong stress intensity factors. This behavior clearly shows that the presence of the hole in specimen is a site of stress concentration that can lead to the initiation and propagation of cracks. In this study, the objective is to see the direction of crack propagation and the influences of notch position on the elastic limit and the file limit in the materials. The experiments were used with several types of crack specimen and the hole in their static loading. Now with the purpose of this study. So we can start by numerical determining by the finite element method stress concentration factor K due to the presence of a circular hole in straight specimen subjected to tonsil loading. Then the investigation was extended to the effect of applied stress and hole size in the stress concentration factors. After that, you can see to study to the influence of the presence of notch and hull on elastic limit and the breaking limit of the test specimens. And finally, to study the interaction between notch and the holes and their influence on the direction of the crack propagation. Now with the three-dimensional analysis of stress concentration in a test specimen with the hole intention, we are interested in this in the study of stress in perforated specimen subjected in axial tensile test. So the hole is considered to be small enough that the stress state away from the hole isn't affected by its presence. Then a three-dimensional geometric model was developed to analyze the distribution and intensity of stress induced in specimens with the host. The numerical simulation is made by the finite element calculation called abacus, and the precision of the numerical result is strongly related to the quality of the mesh around the hole. The mesh has been refined in the region considered critical where high stress concentrations are expected, especially at the interface. Steel has been defined as an elastic material whose mechanical properties are given by Young's modulus and Poisson's coefficient. Can say the value in this table. So the results obtained from this analysis are shown in the figures. The latter presents the distribution of the von Mises equivalent stress and normal in the specimen near the hole. This figure shows that the height stress were located near the interface with the hole at point A and B. Far from the latter, the specimen is totally relaxed from these constraints. Now with the mechanical loading, effect of mechanical loading. So the influence of mechanical loading on the intensity of the equivalence test is given in the figure. It clearly shows that a more intense effort induces a greater stress. The specimen whose level reaches its maximum near the interface with the hole. Then the normal stress SYY places the specimen in tension, whose amplitude increases strongly. The distribution of the normal stress SXX is completely different from that of the component SYY. Its maximum intensity is reached near the interface with the hole. The normal stress in the Z direction put the specimen in compression. Thirdly, effect of hole size. So the stress concentration rises slowly and more and then rapidly with increasing hole size. So larger hole size lead to the strong stress intensity factors. This behavior clearly shows that the presence of a hole in structure is a site of stress concentration that can lead to the initiation and propagation of cracks. After that, in a second approach, we predict the existence of the notch with the three different positions. We considered that the distance between the notch and the hole is equal to the 30 millimeters, including the hole center and the notch in the ligament. The maximum stresses are obtained at the notch and the hole. This shows that the presence of this type of the hole weakness the structure and lead to the increases risk of crack initiation. So we can see in this figure different results with different cases. We can see in this figure that the stress concentration zone at the end of the hole influence the direction of crack propagation. This crack propagation phenomenon only appears when the crack is very close in the hole. We can say that this effect is globally due to crack-hole interaction. In both cases, the direction of crack propagation is always towards to the point of high stress concentration in the model as shown in the figure. So our conclusion. So the stress are located near the interface between the specimen and the hole. Far from the interface, the specimen is completely free from these constraints. Based of the assumption of the spherical hole, the stress distribution levels concentration around the pole, mainly in the y direction. This stress reaches a height level at the point of edge of the hole, A and B. Thus, a crack can be propagated from this point, which presents a real risk of structure failure. The stress concentration factor is sensitive of the size of the hole. It has been observed that K becomes more and more intense in proportion of the diameter of the hole. The normal stress according to the direction takes a height level there. When the hole becomes K, this concentration increases rapidly and becomes weaker and weaker. That the spherical holes are less dangerous compared to the K ones. Crack can be propagated from a point of high stress concentration, which presents a real risk of structural failure. And on the other hand, in the cases the stress does not reach the volume necessary of initiation and propagation cracks, this point influences the direction to the direction of propagation and cracks in the region and leads to stop of the crack propagation. Thank you for your attention and bye-bye.
Thank you for your presentation. Are there any questions? Any questions? Okay, thank you again for your interesting presentation. We can move on with the next presentation. The title is Investigation the Influence of Pre-Existing Crack on the Failure of High Carbon Steel Girders. The speaker is Nick Dugyu. Is the author here? Is the author here? Okay, so I suppose that we can move on with another presentation. The next is studying the wave propagating characteristics of a defected semi-rigid structure near field and far field. The speaker is Tam Zan Zung. Is the author here?
Thank you. I'm sorry. Thank you for the chair, professor, chair, the session for your introduction. I would like to invite all of you hearing the recording presentation here. So I prepared it already.
Okay.
Because the time is very short. Neatly.
You have a time, huh? You have time. So
yes, thank you. But I prepared it already. Thank you.
Okay, no problem.
Hello, everybody. Distinguished guests, professor and scientists.
It's my problem.
Today, I would like to introduce my recent study about structural health monitoring and structural engineering.
Please, the sound, it's a little bit low. Can you please increase?
Characteristic of a defected semi-rigid structure. And there are four parts of in my content. That is the
First is the reason for study. Second is method.
Yes, Dr. Tom.
Result, and finally we have some conclusion. The structure will be.
Can you, Erika, please ask him to increase the little bit the sound?
Okay.
I'm sorry.
Dr. Dong, the
I'm sorry.
volume of the presentation is a little bit low. Could you increase the quality of the speaker, please?
I'm sorry. I can't figure foresee that. So I will present it now live because I have time. Will you please?
Okay.
Thank you.
Thank you.
So I prepared. Okay, hello everybody. Can you hear me?
Yes, we
okay.
can hear you.
Yeah, thank you. Today I would like to introduce my recent study about structural health monitoring, but for the semi-rigid structure in the geotechnical engineering, because that is the title of my presentation is studying the wave characteristic of a defected semi-rigid structure. Now about the
Excuse me.
we have four
Can you
parts.
share the ice cream? I cannot see the ice cream. The screen.
Screen?
Yes. I don't see the screen.
I'm sorry. We asked. Okay. Can you see it? Okay. I'm sorry.
Okay, now we can see.
So there are four parts. There are four parts in my presentation. The reason for the
Doctor,
study.
can you please make a slideshow, please? Slideshow.
Slideshow? No. I think that I had better to present it here instead of my video.
Okay.
The second is about the method, The third is the result, and finally we have some conclusion for it. About the study, you know that the semi-rigid structure, unlike the rigid structure, especially in the geotechnical engineering, that is a soil cement column. The study will be conducted in the near field and the far field because when have some soil cement column have defects or some defects are deliberately created. Including, for example, necking 50%, bulging 20% in diameter. And for example, the low material rigidity, we will conduct it with the 1/3 of the original stiffness. And the velocity response of the pile column could be examined. About the method, we have some, about the model, we have some pile here with some time-dependent loading on the top of the structure. We have some stiffness and the damper ratio as previously cited in the textbook. About the signal, we detect the damage within the time domain analysis and frequency domain analysis. There are 5 factors to be studied here. That is that I prescribed here is a time-dependent loading here. About the condition crack, for example, we have some cracks or some bulging or some necking here, randomly located, for example. And geometry of the crack element and quality of material. This is the material stiffness. And finally, we have some restraint about the partial restraint or fully fixed ratio. There are 5 input factors for it, and That is, the X1 is reduced area or energy. X2 is the loss of friction, for example. X3 is discontinuity, X4 is the low quality, and finally the X5 is excitation source. But I try to input the two uncontrollable factors, for example, the stratification of the soil foundation N1 and the weakness of the wave signal, for example, N2 due to the pile slenderness. And all is in the schematic diagram like this. And this is the slide. We can see the pile in schematic diagram. We have some necking here, we have some bunching here, and we have some, we will estimate or compute the mechanical impedance Z. Z, we can, that is the product of the specific weight, the velocity of wave propagating within the structure, about the area of the cross section, for example, and we we will conduct analysis in frequency domain, and this is the output of the SEP 2000 we used and in the near field. And in the far field, we will use the places in order to find out some wave propagating characteristic for it. Here is the model of the far field analysis. There are two points F and C in the far field, and the assumption is to validate or to find out what is the wave traveling in from the this B point to the F and C. And we come to some result. This you can see in here is the curve of the mechanical impedance plotted theoretically by the formula, and behind below is the response we calculate from the response of the software. We have some review that the frequency will decrease from 5 Hertz to the 1.5 Hertz for the semi-rigid structure. And the velocity decrease from the tip to the head. From the head to the tip, I'm sorry. And there is no variation in the impedance of the semi-rigid column is identified. But in the far field, we compute the velocity of wave traveling within the structure. From A to B, we have the time here. And we take the length divided by the time, and we come to the velocity of the wave is about 340 meters per second. Unlike the structure, rigid structure like reinforced concrete, maybe 1,000 or 3,000 or 4,000 meters per second. And here you can see some frequency domain analysis. We have the left photo is about the pile, and the right photo is about the soil cement column, and about the column with necking here, about the column with bulging and the low modulus of elasticity. We have there is a very difference between the dominant frequency between the two kind of structure. About the velocity of pile, we have told previously that the velocity is 3,007 meters per second. But about the stress in the pile, this is some mistake here. The concrete pile will yield the more the stress here, and the soil cement concrete is smaller, and this is wrongly cited. conclusion, we come to conclusion that the defected semi-rigid structure show no change in the impedance. Some high frequency dominant and velocity decrease from head to tip. In the far field, by consider the vibrational transmission from the defected pile column shaft to the outside medium, the result indicate that the velocity of responsive vibration from the semi-rigid structure propagates attenuates nearly to zero at the distance not farther than 20 meters. So the semi-rigid choice cement column with defects reflect no variation or weakly variation in the impedance. Impedance is the mechanical impedance of the structure. And while the wave traveling in semi-rigid is 100 meters per second, much lower than that of the rigid concrete pile. The response in the far field decays at a closer distance than that of the structure of pile structure. And finally, with the mechanism of the wave transmission via the shaft of the semi-rigid structure, especially for the soil cement structure, is rather weak, and the zone of wave transmission into the far field is much smaller than that of the rigid pile, even we attacked with a heavy driving load, as in this study, 100 kilonewton. So that is my small study here, and thank you very much for your listening and your attention.
Are there any questions? Okay. Thank you again for your interesting presentation.
Thank you.
We can move on with the last presentation of this session. The title is Bonding-Based Approach for Calculation of Shear Resistance of ETS FRP bars in ETS strengthened beams. The speaker is Fu Jung Jun.
All right. Thank you very much for your introduction to the for my presentation. So let me share screen on my presentation now.
Your cup.
All right. So yeah, can you hear me and can you see the screen?
Yes.
Yeah.
Yes, we can see it and we can hear you.
All right. Thank you very much for having me out to listen to my presentation at the SHM&ES conference. My research topic now is the bonding-based approach for calculation of the shear resistance of ETS FRB bars in the ETS strength beams. So the presentation contains includes 4 parts. The first part is the introduction. I will introduce and that rise a problem in my research. And the next part is the literature review. Of course, in the presentation, I just briefly show some research related to my research topic. The part 3 is I will approach to my proposed approach to the bonding base for the shear strength model. And finally, I will give some general conclusion on my presentation. So let's start. Everyone knows now our concrete structures and reinforced concrete structures is much attacked by the environmental factors in Vietnam, not only in Vietnam, but also in the world. So that is the reason why we have to think about the methods to restore or rehabilitate the structural performance. So one of methods is using the fiber reinforced polymers to the bond or the embedded into the members to increase to enhance the capacity of the structures. The reason we use the FRB, because one main reason is because the FRB is not corrosive. due to the growth aggressive environment. My research focused on shear strengthening methods. Currently, we have two popular methods: is the externally bonding and near surface mounting to strengthen in the shear regions of the beams. For externally bonding, we use the FRB sheet or FRB laminate to attach the outside of in the regions. And for the near surface mounting, we make the groove in the shear region, and then we also bond the FRB bar, FRB laminate. But in the two methods, the main disadvantage is the tedious service and susceptibility to fire, high cost and time consuming. And for the mechanical properties, the main disadvantage is the debonding of the FRB composite to the concrete. So that is very crucial issues on the shear strength capacity of the beams. So at the photo below, you can see the shear failure due to the debonding of the strengthening material to the concrete. So they cannot enhance the maximum capacities of the members. That is the reason why in my research we focus on the new methods that can overcome the drawbacks in the previous methods. We call the embedded throw section method. For the embedded throw section method, now this is very new methods, and there are some around 3 or 4 research groups focusing on the method. So in this method, we drill the hole along the section in the shear region, and then we also put insert the FRB bar or steel bar inside the concrete section. So with this section, we can see that because the bar embedded inside the section, so there's no corrosion attack or also no fire attached to the reinforcement. And almost in the previous research, they showed that the capacities of the EDS methods is much higher than the previous methods for the shear strengthening of the RC beams. Now, and then in entire of my research, so I focused on the FRB material that can be used for the not only the shear strengthening but also flexural strengthening. But in this study, I just show you the part of my research project. So let's move to, in the I saw one previous study of Barros et al. 2012, and in this research he conducted 3 groups of beam with 3 groups of strengthening methods, the EB and SM and ETS. So the final result, they show that the shear strengthening efficiencies of ETS is very much higher than the previous method due to some reason. The first is the bond efficiency between the materials and concrete is higher, he assured. And also for the failure is balanced rather than the previous method. So, but in his study, there's some still this not good point. So, for example, that the debonding of the FRB bar to the concrete is still occurred. Yeah, we can see in the photo that they can capture that there's slip there. It means the debonding failure occurs, making the shear failure, and that is the reason why the strength values in the CFRB bar is not reached the ultimate value, the maximum capacity of the FRB. It cannot. And my research question is how to improve the strengthening capacity and also avoid the debonding in the beams. So in my research, I will use the anchorage at 2 ends, anchorage to the ETS bar at 2 ends. I use steel anchorage to make sure that the bar is not debonded during the load increases. And for the shear model for the beams, everyone knows, we know that the truss analogy is now very popular, and that is available in the code, the guidelines like ACI or JSCE. But there are many previous studies showing that the trust analogy using in the ACI or JSCE can very underestimate the actual values. So in my research, I will propose the new approach that can estimate accurately rather than the models in codes. So the figures show that the sheer contribution of ETS that make the comparison between the JCE, ACE, and UIDAS model. And as I told you, the values for the estimation is very underestimate rather than the experimental values. So bonding by approach, yeah. First, we have to know that because I told you that the debonding govern the shear failure of the beam. So I mean the bonding efficiency between the FRB and concrete will be decided for the shear capacity of the member. First, we conduct a group of the pull-out test to measure that, to estimate that what is the bond model can represent for the ETS bar to concrete. And so you can see that the configuration and real photo for the testing. And in the configuration of the pull-out test, we use the many strengths to attach along the bars, and then based on the strength value, we can compute the bond stress, the local bond stress and local slip based on the equation. So based on the result, I will propose the bond model based on analytical results. This is show you the first is strength distribution along the bars, and also this is the bond slip, bond stress and slip relationship. Yeah. Experimental bond slip relationship, and we can see that strength profile was non-linearly distributed along the length, and values of the transfer length and the strength increase at the increasing of the gripping tensile force. And in my research, I proposed that equation that can be satisfied for the calibration of the bond test results. So then we will use that equation to propose for my bonding by approach equation. Yeah, let me show you the idea for the bonding by approach. The bonding by approach is the first based on the bonding between materials and concrete. Then I will convert the bonding by to the shear behavior of the beam. Yeah, and then from the bond first, we will compute the strength capacity of the FRB bars. And the main idea is the shear region of the beams, and then we will consider what is the equivalent concrete block based on the pull out. And then if we know the pull out failure and pull out force, we can estimate the shear contribution of the ETS bars. And in this research, I have to approach. The first, I will use the mechanical approach. This means I will find the fracture analysis equation based on a mathematical analysis. And the second, I will propose the fracture analysis based on the regression. And this is the final shear contribution equation for the ETS bars. And so if we know the GF, we will know, and properties of the materials, we will know the shear contribution. And for the GF, we can define by choose equation approach. Yeah, that's what I have so clearly in the paper. So this is the model verification. And I collect the test data and also my test data in the previous study. And I conduct the two approach. The first approach is mechanical approach that I show you the equation of GF based on the mathematical analysis. And the second approach is the regression approach that we make regression procedures to propose the GF equation based on empirical factors. And the final results give the comparison between the proposed model and experiment. And we can see that the bond factors is mean the maximum bond stress and its big slip affect substantially the prediction of the results. And the mechanical approach provides very good agreement rather than the regressing approach. Although regressing approach provides the lower prediction than the mechanical approach, but it can be suitable which at the case we don't know the bond factors, like we don't know the maximum bond stress, we don't know the slip in the specimen. So here's some conclusions. First, there is a novel and promising study that can estimate the shear strength of the EDS strengthening or retrofitting system in the RC beam through the bonding-based approach. And for the mechanical approach, if we know exactly the tau m, it means the bond stress, as SM, it means the slip and peak bond stress, the proposed bond model will demonstrate the substantial efficiency in prediction of the results in the comparison to the experimental data. And finally, the regressing approach for less accuracies, but it's still reasonable for calculation. In this case, we don't know the accurate bond factors as I saw before. And finally, thank you very much for your listening to my presentation.
Thank you for your presentation. Are there any questions? Okay. Thank you again for your interesting presentation. Okay. This was the last presentation, so we can close this session. Thank you for all the participants.
Okay, thanks, Erika, for your contribution. And okay, now let's start with the new session, the session number 2, crack analysis for engineering structure. So the first presentation, so reducing shrinkage and improving cracking resistance of concrete by using ash, the author Nguyen T. Bishte. So is here. I don't know if it's here or no. Yes, Kong, do you know this author? Or?
Nguyễn Thị Bích Thủy. You there? You here? Yes. We invite the presentation of Nguyễn Thị Bích Thủy with the number 1017.
Yes. So
I didn't see. Yeah. I don't see. Or we can move to the next.
I would like to move to the next presentation by Erika McKinney, effect of damage by not in the vibration response of homogeneous and heterogeneous beam models. Can you, Erika, please start or share your presentation, please?
Okay, thank you, Samir. I will going to share my presentation.
Okay.
Erika, finish.
This is the outline of my presentation. In the first part, experimental campaign, then I will describe the finite elements modeling, and finally the main results will be The existing structure of buildings and of high-performance constructions like bridges often presents damage due to chemical processes of aggressive environmental conditions, and sometimes they cannot be able to support new design service loads. Damage detection and health monitoring of structural elements are currently relevant topics in civil engineering. The evaluation of the residual capacity of the existing structures based on response to vibration has gained popularity in recent years. The deterioration of structural elements subjected to environmental chemical agents like pollution or to consequences of unforeseen state of damage due to impact loading is becoming an emerging duty of research in civil and mechanical engineering. The aim of this work is both to acquire information on real structural elements through a laboratory experimental campaign on beams in scale and to underline a number of aspects that can be useful in practice. In this work, the experimental behavior of damaged beam models has been analyzed by dynamic tests of free vibration, adapting 6 beam models, 4 beams as homogeneous model, 1 undamaged and 3 with a different degree of damage by notches, 4 RC beams as heterogeneous models, again damaged by notches. The damage is located in the middle of the span. The choice to damage the beam models by notching derived from the purpose to investigate the effect of a localized damage with high reduction of global stiffness, such as local detachment or local corrosion. The vibration test was chosen because it allowed describing the fall of frequency values at the increase of damage degree. The fundamental concept behind monitoring by vibration is that the structure's physical properties influence the dynamic characteristics. So when a structural element is subjected to damage, its dynamic response will change. In a first phase, experimental tests were carried out on slender beams in scale with a ratio between height and length equal to 1/16. Beams were built with an homogeneous material as marble from Carrara in Italy. A mechanical apparatus was used to simulate the constraints at the ends as in conditions for a simple supported beam. Rotation was made possible by mechanical bearings attached to 4 steel supports bound to a steel plate located on a hard rubber plate. The mechanical system was used for analyzing both the non-damaged beam model indicated as damage degree D0 and the elements damaged by notches as 3 beams with concentrated damage by notches at midspan, labeled as N1, N1B, and N1 with the capital letter. The experimental dynamic test was performed by means of a technique where the acceleration of the element caused by an impact of an hammer at a fixed point was recorded by an accelerometer. The impact point was placed at a distance of 37.50 millimeters. The piezoelectric accelerometer was positioned at 5 different points placed at different intervals. For each location of the accelerometer, a set of 10 hits was made and the average value was obtained. The envelope of frequency response functions was obtained using pulse software. The ordinate axis stands for amplitude of the frequency response functions in terms of acceleration and the logarithmic scale, while the abscissa axis stands for frequencies. Functions have peaks at the natural frequencies of the beam. A function referred to as coherence was elaborated during dynamic tests in order to monitor the absence of noise in the vibration results. The suitability of the experimental setup was checked by the evaluation of the theoretical values of the natural frequencies for the first 3 modes of vibration carried out prior to the experimental study. The earlier Bernoulli expression was utilized for the evaluation of the circular frequencies of beam, supposed as slender and homogeneous. The table reported here shows a comparison between the natural frequencies obtained experimentally on undamaged beam model and theoretically considering the Bernoulli equations and by modeling with finite elements. It is possible to notice a good agreement between the data obtained by the experimentation and the ones given by theoretical analysis that confirms the validity of the system used for the simulation of the constrained conditions. The frequency response functions were recorded for each damage degree. From the analysis of the envelopes of the frequency response functions, it is possible to state that for all tested beam models, the frequency values tend to decrease progressively parallel to the increase of damage by notch. It is possible to verify that the concentrated damage causes a reduction of the experimental frequency values. In particular, for the first modes, we can see a constant variation in percent equal to 25%. The frequency values of the second mode are obviously influenced by the modal form, which provides a node as the midspan of the beam where the damage is located. In the second phase, experimental vibration tests were carried out on reinforced concrete beam models with free ends. The Earth's beam model had a trapezoidal cross-section and length of 1000 millimeters. Beam was reinforced with 2 diagonal steel bars of diameter 6 millimeters and 2 with diameter of 12 millimeters without the presence of stirrups. Experimental dynamic tests were carried out on the different beam models using a specific impact hammer to trigger the structural element and a fixed accelerometer to measure the acceleration of the system. The dynamic test was performed recording the response of the structure in one position inputted by impact hammer in 9 positions with an average of 10 beats per location. The effect of localized damage by notch all over the midspan section of the Earth's beam model was experimentally evaluated. 3 different damage steps, D1, D2, and D3, increasing the width of notch was considered. And the notch was placed at the midspan section of beam. The envelope of experimental frequency response function diagrams with measures of vibration recorded by the accelerometer varying the points of impact in a number of selected marks in the undamaged condition are contained here. It is possible to observe that the peaks correspond to the natural frequency of beam in the undamaged condition. Also in this case, during tests, experimental results were verified comparing the experimental data with the preliminary theoretical one in terms of reduction of frequency value to limit dynamic response error due to imperfections of the experimental apparatus. It is possible to observe that results given by finite element modeling fit adequately the frequency values given by experimental analysis. Dynamic tests were performed for each damage phase and the natural frequency values were acquired. Here, the experimental diagrams of frequency response functions at various states of damage with the vibration measurements recorded by the accelerometer at a number of impact mark points are shown. In the table, the average values between measurements of frequencies for each position of the impact point are summarized together with the standard variations of frequencies in relation to the various degree of damage. It can be seen how the increase of the notch width causes a decrease of the frequency value. Referring to the frequency variations, it can be observed that also for low damage degrees, the variation is significant, showing a level equal to about 24% for the first mode of vibration and 8.5% for the second mode of vibration. In correspondence of final damage level D3, the peak was reached with a value of about 58% for the first mode of vibration and 15% for the second mode of vibration. Finally, numerical modeling was performed by finite elements. The ANSYS code was used for the modeling of the homogeneous and heterogeneous beam models. Elements made by solid bricks were used to model all the materials adapted, including marble and aluminum at the ends for the homogeneous beam, concrete and steel for the heterogeneous earth beam. Marble and concrete were modeled using the brick elements labeled as solid 65. The aluminum was reproduced using solid 185 elements, having Young modulus and Poisson's ratio equal respectively to 70 kilonewton on square millimeters and 0.3. The steel reinforcement was modeled with the use of the beam 188 elements. The numerical analysis has been developed assuming constraints adopted in the test, simply as a simply supported beam for homogeneous models and with free ends for the RCB models. In addition to the book components, element combine 14 defined by two nodes, aspirin constant K and damping coefficients was used in the numerical modeling in order to model the suspension springs of the beams, simulating the same free beam conditions during vibration test. Finally, during the modeling procedure, also the mass of the accelerometer was considered. The accelerometer was taken into account in a simplified way as a point with mass of 15 grams. The purpose of the analytical study is to extract the frequencies of the device and the modular shapes as the degree of damage increases. For each finite element beam model analysis was performed to derive the first four natural frequencies of beams corresponding to the experimental modes measured by the dynamic experiments. The most shapes provided by the finite elements modeling of homogeneous and heterogeneous beam models at each the damage degree are shown here. Results of finite element modeling were compared with the ones obtained by experimental tests in terms of frequency variation in percent. The table on the left gives a comparison between the values of frequency obtained by finite elements modeling of the homogeneous model and by experimentation. Considering the first three modes of vibration, it is possible to notice that the approximation of numerical results is adequate with variations varying from 0.07% to 40.65% in relation to the experimental results. In the table on the right, the values of frequency evaluated by experimental tests and finite element modeling are compared for heterogeneous RCB model. In this case, for the first mode, the numerical modeling gives results that are in good agreement with the ones obtained experimentally, with a percent deviation for damage degree B0 and B3 equal to respectively 0.66% and 1.30%. Similar values of variations were obtained for the other first formulas, with variation in percent varying between 0.04% to 5.89%. So, to conclude, this research led to the following results. The first result is that the reduction of the value of frequencies is connected to the increase of level of damage with a shift of experimental frequency response function diagrams. The second result is that in the homogeneous beam models, the comparison between experimental and finite element modeling results permit to verify an adequate agreement taking into account the difficulty to simulate in the finite element model the mechanical imperfections of the measurement apparatus. The third result is that in the case of heterogeneous beam models as LCB models, the comparison between experimental and theoretical data by finite element modeling permits to verify a perfect agreement between experimentation and numerical modeling. Thank you for the attention.
Okay, thank you, Erika, for a nice and long presentation. Okay, no problem. So if someone has a question, so you are welcome. If there is no question, we can go to the next.
Excuse me, can I have the questions?
Yes, of course, yeah.
Thank you very much for your very interesting presentation. I am interested in what is the bond model between the reinforcement and concrete that you use in your simulation?
We suppose a perfect bond connection between steel and concrete.
Yes. What is the bond model?
Sorry, I don't understand.
The bond model.
The boundary.
You mean the boundary condition or what?
Boundary condition, okay. For the homogeneous beam model, we suppose that the beam was simply supported. So we consider the hinges condition at the end. For the heterogeneous beam model, we suppose a free hand condition. So, but we consider a spring at the ends of the beam. Okay.
And how do you estimate the stiffness of spring in your bond model?
Okay, we suppose that we estimate the spring of the spring coefficient by experimentation. Okay, we tested the support system with the tensile test, and then we suppose we estimate a spring coefficient. And then we compare the numerical results with the experimental results by dynamic test to understand, to verify the coherence of this coefficient.
Yeah, thank you very much for your answer.
Thank you too for your question.
Okay, if there is no more questions, then we can go to the next presentation. Who is the next? Okay, I think it's here. Response of concrete filled double skin tube consume their blades Lloyds by Tin Du.
All right. Thank you for your. Thank you. All right. Can everyone hear me?
Yes, you can.
All right. Thank you. Thanks.
Yes.
I've been waiting for so long. It's a long day. Hi everyone. I'm Tim from Australia. It's already 7 o'clock at night, so I will run very quick today. I'm a blast engineer at Cancer, Australia, and my work's almost about the blast response of the structures. but my presentation today just focus on the, I wish mostly so you got the videos that then go into any equation or any technique. It's very hard for people to understand. So just have a quick introduction about KNC. If you're working in the impact and blast engineering area, you may know KNC is one of the famous companies in the world. We are doing the threat assessment, protective design, and we do the modeling and simulation. We do software development and apply research as well. And here is the example for the blast response of the structure. We did the real scale blast test for US Embassy in Iraq. This is the entire building. It's a full scale building, and this is the TNT chart. It's how the structure, sorry, let's come back. The video doesn't work. Maybe just go a sec. Here's how the structure responds to the blast. Click. I don't know, I run several times, but maybe it doesn't work today. Come on, man. Here, just if the video doesn't work, so just go quickly. We did the full scale blast test for the US Embassy in Iraq and in other countries as well. And here is the other example for the impact test. We run the vertical impact to the structure. In that, we have our structure in this side, and we use the real vertical to impact to the structures. But I don't know why the video doesn't work today. So I just run quickly to my summation and to my study. My presentation have three main sections: the literature review, the numerical investigation, and the research output. For literature review, you know, nowadays recast concrete structures is one of the very famous construction technique in the world. And here is an example. If you have the column structures, you divide the column into several segments. You prepare everything in the workshop. You bring into the construction site, and then you put on top of each other. You use a tendon to connect on the segment together, and then you have your structure here. So if we prepare everything in the workshop, we can significantly reduce the construction duration. We enhance the on-site efficiency with diminishing the environmental impact. And we also improve the construction quality because we did everything in the workshop, so we can 100% control the quality of our structures. So this is the advantages of segmental structures. And here is several examples we have been introduced in the world, but we only concerned about the dynamic behavior and capacity of these structures, especially in the US. And we always worry about the blast. I mean, the terrorism. They may attack these structures, and the collapse of this one may cause more fatality. I mean, more people are gonna be dead. So we have to protect these structures. And we did several impact tests. Here is the normal RC column. If we impact to the column, we have the flexure crack, we have the C crack, and how this structure responds to the impact. I don't know why the video doesn't work. I have a lot of video to want to share you guys, but it's so bad. So don't be worried. And we did the impact test to the column. We have several column here. We impact to them at the mid span. We impact to this joint. If you guys can see the video, maybe I will send you guys a presentation after the conference. We can see the column significantly open, and then it's returned to this position. Rather than that, if you see this column, when you hit the column in this way, it's significantly damaged and it's gone. But for this type column, when you hit it, it's open and then it's returned back to its original position. So it's the advantages of that type column. And then I don't know, I'm sorry because I prepare a lot of video. I did present that worked many times, but today I can't really show. Here is the another example. If you hit the column here at the segment, we can see a significant open at the joint. So in the video, we can see if you hit that column and then it's open and then it's returned back, it doesn't fail like a normal column. This is the most advantages of the column. I can't set a video, so we have to move on. And here is the blast response of the seventh column. If we hit the column with the blast load here, we have the expansion of the section. It's quite different to the static load. In the static load, you hit the column with the static, you have the flexural crack in this side. But for the blast, when you hit the column with the pressure, we have the expansion of the column in this direction. And then after a few milliseconds, you're gonna have the concrete spalling at the back of the side. And here the damage. You hit the column with this in this side, you have the damage here. And if we use the steel tube to cover the column, so we don't have any damage. Even the concrete damage, but it still stay inside the column. So this column is still protected, so it will not fail. This is why the steel cover can protect these kind of structures. And again, the video doesn't work. We move on. So from the previous work, we develop our column. We remove the inner core concrete. We use another steel tube. We develop the model in LS Dyna. We run with the blast load. This is the numerical result compared to the experimental test. It's very well comparison here. And then we compare the segment column with the normal concrete fused steel tube column. If you can, as you can see here with the normal column, we have a significant crack on both sides of the column. But for the segment column, we don't really have any damage because it's open and then it's returned back. So we don't have any flexural crack. And here the formation, because we cut the column into several segments. So we reduce the stiffness. And when we reduce the stiffness, we have higher displacement, but we have less residual displacement. And we consider for another a different factor as well. We divide the column into 3, 5, or 7 segments, and we compare the displacement is quite similar. And if we use more segment, we have less concrete damage, of course, because we have more opening zone. It will open more, and then we have less damage. And here we consider different hollowness ratios. And if we reduce the concrete core, as I say again, under blast, we don't have any. Normally, we have the crack in this side and this side of the section. But even we apply the blast in this way, we don't really have any crack in this side, but we have a crack in that side. So this is why we can see the crack here. It's very different compared to a static load. And here is another example for different tube thickness. If we change the tube thickness, we don't really have any difference. It means even you use 5 mil tube or 10 mil tube or 20 mil tube for the column, the damage of concrete is very similar. Here the conclusion. I don't think I have enough time to read on the conclusion, but just so you guys on the screen, if anyone have any interesting question, just raise question. Or you guys can. Here's on my previous work for my PhD study. And here's my email address if you guys feel interested in, and just send an email to me. I can share the work, or I may share a presentation if you want to see the video. Thank you.
Okay, thank you for your interesting presentation. So if someone has a question or...
Yes, I have a question.
Yeah.
Can you tell me what the concrete material do you use in the simulation?
Thank you. Thank you very much for the question. It's the concrete material for the dynamic load. I mean, for the impact or blast, it's very different compared to a normal concrete. As you know, if for a normal concrete structure, if you compress. You design the concrete for 40 MPa, for example, and under static compression is 40 MPa, but under static it may increase to 100 due to strain rate effect. So can see, let me just share screen again. Just show you. Today have so many trouble with the video, but can see Australia. We are part of the SHM&ES, and we develop a very detailed dynamic material. This is one part of our work, and we developed that material for the US government. I mean the Department of Defense, because we consider the US not we. I think US they always have the problem with the blocks, and we developed the material for them, and it's been approved by the Department of Defense, and you can see concrete model. But if you go online, you can really see. You just type can see concrete model. You can see everyone in the world currently. We like 30% or 40% of researchers they want to use can see concrete material. Yeah, thank you.
Right.
I have more question. How about the strain rate effect of your model? Strain rate.
Yeah, thank you.
The strain rate effect to the dynamic factor. I think if you choose multiply case of the velocity, I think the dynamic factor will change. How
yeah,
can
of course.
you input in the model in Abacus to simulation the concrete with tools?
Yes, of course, because we say strain rate. I mean, normal the static load, the strain rate is just around 10 power minus 6 meter per second. But for the dynamic load, I mean, for the impact of blast, the strain rate can increase to 200. And in the model, we can consider that one. And we currently use Aristotle. And for concrete material model, they allow you to put a curve for strain rate effect. So you just define in your model, say with 10 meter per second strain rate effect, you're gonna have this kind of dynamic increase factor. And then for the blast, it's 100. So you have another strain rate effect. And the dynamic model allows you to put that equation, I mean that curve into the model. So if you use Aristotle, it's very easy function. They allow you to put that one into.
Okay.
Thank you.
Okay.
Yeah.
So can I have question?
Yeah. Okay.
And thank you very much for your presentation. So in your study result, you show that when you increase the number of the segmental segments, the displacement will be close, right? I'm not sure that
I think the displacement is gonna be higher.
Yeah, but not much, rather than the smaller amount of the segment.
Yes. Let me. Yeah, it's a very good question. Thank you, my friend. Where that should be here.
Yeah,
right.
Yes.
You know, because for the dynamic load, the impulse is quite important. I mean, the duration of the load. Let me turn that one on. Just wait for a second. I have to move to that here. So a pen. So for the blast load, where is this? So if you hit the column with the blast load, you have the opening here and opening here, right? So if you divide the column into several segments, you have 1, 2, 3, 4 segments. So you have 4 different opening area, and then this one you have a little bit higher displacement, but it's not really significant because you hit the column with the same impulse. You know the impulse, right? The load gonna always have the big pressure, and then you have the impulse. and the impulse is quite similar. And then this why we have really nearly similar displacement. But yeah, we have, because you reduce the stiffness, so you have a little bit higher displacement. This is the reason. But I'm so sad because I can't really share the, I mean, I have a lot of video because today everyone just saw the equation or something.
Explanation is very clear. Yeah, I now can understand clearly. Thank you very much.
Yeah, thanks.
Thank you for nice presentation. Now we can go to the next presentation. So next presentation, it's the superplastic behavior of AA 7075 aluminium allow under the impact of temperature and strain. So Nguyen Man Tien is here, or? Yes, Kong, do you know this? It's D2.
Nguyễn Mạnh Tiến. Gì hả? Nguyễn Mạnh Tiến. I didn't see this author. Simi, if he not here, you can move to next presentation.
What time is it now?
Now it's
okay, it's time also already gone.
Yeah, 3
So
p.m. in
next
Vietnam.
presentation, so thermal crack in concrete structure, the basic issue to be understood. So Kit Boy. Yes,
everyone.
it's here.
Can you hear me clearly?
Yes, are you here? Yeah.
Thank you.
Yes, can you share your screen, please?
Yes.
Okay.
Please wait a moment.
Okay, now, okay, perfect. Okay, perfect, yeah.
Hi everyone. My name Bùi Anh Kiệt from Ho Chi Minh City Open University, Vietnam. Today I'm pleasure to introduce a review of our work. The title of the presentation today is Thermal Cracks in Concrete Structures, the basic issue to be understood. Our authors, including Nguyễn Trọng Trước and Hoàng Quốc Long from Institute of Special Construction Engineer from Liquidon Technical University, and me, Bùi Anh Kiệt, from Faculty of Civil Engineering, Ho Chi Minh City Open University. So the contents of the presentation today include 5 parts, from introduction to reference. Let me show you for the introduction. This is the mechanism for thermal cracks in mass concrete caused by temperature difference at an early age. As you know, at the beginning, due to the hydration heat, temperature rise inside the concrete blocks. So the inner zone, the temperature will be higher than the outer space. The outer surface were contacting with the environment, such as air, ambient, or water temperatures. So after the temperature inside the concrete cool down, the outer surface will be cooler more than the inner, and it's called the contracts. This is the mechanism cause the cracks when the tensile stress higher than tensile strength of concrete at the same time, at the same age. And for this case, our study mentioned deeply on the effects of hydration heat and the conditions of environment. This here cause the including air temperature and water temperatures. This called the convection effect. So our study, the objective is control the thermal cracks for mass concrete, such as concrete dams or mass foundations, etc., and for pavements or concrete slab working in the critical temperature environment. So the first time we need to know how to recognize the thermal cracks. So this is a summary. It's very easy to understand. For the concrete block, the cracks normally occurs on the surface within several days after removing from work. When at this time the temperature gradients is higher, so this is the possibility to occur the cracks is higher than other moment. And for concrete slab, normally occurs. The first is the directions. Direction is perpendicular to the longest axis. This means the longer axis compared to others. And this normally occurs in the first summer or the first winter of the first year after construction. Yeah. This is the some image we can see, and based on the experience, we can have some identify like this. And some criteria used to evaluate and control thermal cracks. We have here. I show you three standards. The first is TCVN from Vietnam standard. Another one is from Britain standard, and the last one is Japan standards. So in Vietnam standards, TCVN like this, there is control the temperature different should be less than 20 degrees Celsius, and the models of temperature gradients MTs less than 20 degrees C, 50 degrees Celsius per meter. Another one for Britain standard, they have equation to define the maximum temperature difference, allow for avoiding thermal cracks. In these equations, epsilon is the ultimate tensile strength of the concrete at an early age, and alpha is the thermal expansion coefficients of concrete. For GCA, they define the thermal crack index by this equation. The ratio of maximum thermal stress, the maximum tensile strength of concrete to maximum thermal stress due to cement hydration at the day T. So for this, the criteria like this, for prevent cracks, the ice critical should be larger than 1.5, and the possibilities of limited cracks, the thermal cracks index should be below, in the range of 1.2 to 1.5, and limiting the occurrence of dangerous cracks, the thermal cracks index should be in the range of 0.7 to 1.2. So based on the standard we use, we can reference some criteria like this. In our study, previous studies, we mentioned deeply on the FEM by using some applications such as Abacus and ANSYS, and another one. Sorry, and this one is the equation, the differential equation to express the thermal conduction equation here. In here, mention about the three direction in Cartesian coordinate with kx, ky's, and kz is the conductivities coefficient, and also internal heat source QV also mentioned in here. The specific heat of concrete also mentioned here. This is the general equation used for conduction. And the right hand side, this is the flow chart to conduct the thermal simulation in FEM for acquisition parameters, including the using the transient thermal, using the element type with 8 node or 16 node also, and apply the reference temperature, assign the material, including thermal conductivity, specificity, and density. Create the geometry and apply the initial temperature. The initial temperature here is mean that the placing temperature, and apply other boundary condition. The boundary conditions is including the solarization and convection also. After that, for the solution, and we get the result here, and compare to the some actual monitoring. After that, we have some proposals to minimize the thermal cracks. Here is we show some option can be used. The first, using chemical admixture to delay the temperature reaching the maximum value. This is one option we can consider. The second, selection of the appropriate moments of placing concrete. So in this case, we can place concrete at night or early morning to reduce the initial the ambient temperatures. The first one, using lower the initial temperatures of the concrete mixture by using reducing the temperature of aggregate using ice instead of waters. It's been that pre-cooling, and using liquid nitrogen to cool down the concrete mixture. So this is the example for using the liquid nitrogen injected into the containers truck. We can use this one is one option here. And another one, we can use simulations to control the thermal effect before conducting placing. This one, we use the cement replacement materials. For example, in the lab pictures, we can see we use 100% of cement. Others, we use 20% natural porcelain class F replacing cement. So when we use the material replacing cement, we can see the temperature, maximum temperature here is the lowest around 13 degrees Celsius. So when the temperature reduces, it means that the possibility to occur the cracks, thermal cracks, is lower. So this one is the is one of the optional for control thermal cracks very effective. Another one is using cooling pipe system. In these figures for the another previous study, we use with the water temperature in pipe cooling with 10 degrees Celsius, 15, 20, 25 degrees Celsius, and also without using cooling pipe system. So you can see clearly the effect of the cooling pipe system and its water temperatures through the pipe. If we use the lowest temperature of waters through the pipe, the temperature is the maximum temperature is lower compared to others, and the gradient between from the initial, for example, here we start at 25 degrees Celsius, and here just around 55 degrees Celsius. It means that the temperature degree gradient is lower than all other case. Another option also considered in our study is using surface insulation by using other material for polyethylene, polyethylene foam, or sand layer or waters, and pull up or tarpaulin. So here is an example: the left and the right hand side with down and with using the insulation layers. In case of not using insulation layers, we can see that the temperature gradient between the outside and the center of the concrete block around 26 degrees Celsius. First, when we use only 1 centimeter thickness of polystyrene layers, the temperature reduced to 10 degrees. This means that the temperature different just around 16 degrees Celsius. So we can conclude that when we use the upraised surface insulation layers, and the tail thickness also affect more for the temperature difference in the concrete block. And another one is reduce the thickness of the concrete crackings. This one also the option we can consider. In the left picture, we use with the 4 meter thickness layers of concrete, and the right hand side only 2 meter thickness layers. So we can see that the maximum temperatures in the concrete block in two cases is different. When we deal with the two thinner layers, the temperature will be lower. The maximum temperature will be lower because it can contact more with the air ambient based on the convection coefficient. So this one, the temperature is lower compared to using with the deeper layers. After we consider some option for avoid cracks, we also mentioned we propose some option for repair thermal cracks. In case of cement concrete pavements, may use compatible material or demolitions of cracks or dump area to replace by new cement concrete. Another for mass concrete, it depends on the crack width, the crack depth, and the operation in the futures. If the crack width is small, for mass concrete, it will not affect to the strength of the and also workabilities of the structure. First, in case of the crack width is large, upstream should be used for repair the cracks. Some conclusion here. The conclusion mentioned the studies deeply concentrate on how to control and prevent the formation of thermal cracks. Alternatives or options based on each type of structures are proposed. So in case of mass concrete structures, should be optimized factors affected to thermal stress, such as cement content or type of cement, the initial temperatures of concrete mix, or also curing methods by using the insulation layers. For cement concrete pavement, should determine carefully for the technique of the pavement and also for the dimension of the pavement. And here is some reference used for the paper and also for the presentation today. Thank you very much for your listening. Thank you.
Okay, thank you very much for your presentation. So if someone has a question, you're welcome to ask. Yes, any question? If there is no question, we can go to the next presentation.
Okay, thank you for all. again.
Okay, okay, yeah, thank you very much. Thank you. Okay, now the next presentation, experimental investigation on flexural behavior of reinforced lightweight concrete slab using recycled expanded polystyrene by an. It's here, you are here?
Yes, we are here.
Yeah, okay, so
Well,
now you can share your presentation, please.
okay, good afternoon, ladies and gentlemen. Let me share our video file.
Okay, yeah.
Ladies and gentlemen, the research topic is experimental investigation on flexural behavior of reinforced lightweight concrete slabs using recycled expanded polystyrene. Lightweight expanded polystyrene concrete EPSC has been investigated and used contributed to energy saving and sustainable development. EPSC is formed by components such as cement, water, light aggregate EPS, and admixtures. PS concrete shows a good characteristic in thermal insulation, acoustic insulation. Besides, EPS with have.
Sorry, can you hear well?
It's okay, it's okay. Okay, go ahead. Okay.
To reduce the weight of concrete. For building construction, especially in Vietnam, it's mainly used for non-structural members.
Yes, sir, we can't hear your presentation, please.
To ensure the sustainable development and use the EPS concrete for testing the ability EPS concrete using recycled polystyrene. An experiment campaign has been carried out to investigate the flexural behavior of EPS concrete one-way slabs. The composition of EPS concrete material is shown in the table. To determine mechanical properties of EPSC, cubic and cylindrical chambers were mixed in the same batch with the concrete used in slabs. The main reinforcement in longer direction and distribution reinforcement in shorter direction. 3 full-scale slab specimens named M1, M2, M3 were tested. 4-point bending scheme was applied. The loading was performed in displacement controlled by hydraulic jack, 3 LVDT, linear variable differential transformer were placed up to support and a midspan of slab. 9 chain gauges were attached to the rebar. The experimental results in the figure show that the load deflection relationship of the 3 specimens are well consistent. Further analysis are carried out on the results of specimen M1. The slab behavior can be categorized in the three stages. Stage 1, before correct appearance, the reinforcement and concrete still behave in the elastic phase. This stage ends at point A, when the load applied meets the cracking load. As the transition from stage 1 to stage 2, the curve is almost horizontal. The entire loading is transmitted from concrete to the rebar, which explains a sudden increase in the rebar stress chain behaviors as observed in the figure. Stage 2, after a crack occurrence, the crack grows with increasing load. Tensile force in slab is mostly supported by rebar. Stage 2 terminates at point B, at which the reinforcement rapidly hits its yielding limit. Stage 3, segment BC, the deflection of the slab increased rapidly due to the reduction of slab stiffness caused by the development of the multi-crack. This stage ends at point C when slab starts not being able to sustain the loading. Point C refers to ultimate load of the slab. The results show that the cracking load corresponds approximately to 16% of the ultimate load, in line with typical concrete slab experience. Due to Eurocode 2, the allowable deflection and the limit of the crack width can be determined. Following those values, the serviceability limit loading of the slab to ensure the condition of normal use reach around 4 kN. Conclusions: the behavior of reinforced EPSC slab is close to that of conventional reinforced concrete slab, representing by failure regime and capacity in ensuring normal use requirement. The serviceability loads corresponding to the allowable deflection and maximum crack width for slabs spanning less than 2 meters are approximately 45% of the ultimate load. The load-bearing capacity of 100 mm thickness reinforced concrete slab made from EPSC with the density of 1,200 kg could reach over 4 kN by square meter. Thank you for your kind attention.
Okay, thank you very much for your nice presentation. So if someone has a question, you're welcome. Yes?
Yes.
Okay.
Can you hear well?
Yeah.
Excuse me, can I have a question?
Yeah.
Yes. Can you show a slide of the strength response in reinforcement of the slabs?
Hello, can you hear well?
Yes, the strength of reinforcement.
Yes, can you see well?
Yeah, I can see, but I don't know why. What kind of strength that you measure for what specimens of the strength values? Because I see that the load deflection relationship is slightly identical between the specimens, but for strength response is large different, is significantly. significant difference? Can you explain?
Hello? Hello?
Yes.
Yes, you can go ahead.
Yeah. Yeah.
Sorry, can you repeat the question, please? Hello?
Yes. The strength values in the reinforcement that you measure is only one specimen M1, right? Because I see many curves in that photo, in that figure. So if my question is not clear, it's okay. We can move to another question or the next presentation. We can discuss later, no problem at all. All right, we can discuss later. I can email to ask you.
I think, can you hear the question, please? The presenter, can you hear the question or no? I think yes.
Sorry.
Yes, you can't hear the question, or can you write the question, please? Can you write the question?
So I think I will, we can discuss later after the conference. I will email to ask to discuss. No problem.
Okay.
Thank you very much.
Okay, thank you very much. There is no further questions. Okay, now we go to the next presentation, experimental and numerical vibration analysis of healthy and corrected pipe. Mariam.
Thank you, Mr. Khatir. So good morning, everybody. I hope that all of you are doing well. I will share my presentation.
Yes, can you? Yes, you can share, and I don't know if last
no
one
problem.
has to withdraw this presentation, please. Can you share, Mariam?
I can't.
Please, I don't know his name. Please, boy, can you withdraw your presentation from the system, please? Okay, now you can share. Okay.
Okay. I'm searching. I think good morning, everybody, and thanks for being here. Before
But I
starting,
cannot see. I can't see your. I can't see your.
Wait a minute, please. Can you share it, Samir? Good morning, everybody, and thanks for being here. Before starting my presentation, I would like to thank the scientific and organization committees. My name is Mariam Segini. I am Algerian and I live in Oran. Currently, doctor in civil engineering and lecturer at the University of Science and Technology of Oran, Mohamed Boudiaf, Faculty of Architecture and Civil Engineering, and I am member of the Laboratory of Mechanical Structure and Stability of Construction. So today we speak about the experimental numerical vibration analysis of healthy and cracked pipes. I will start this presentation by an introduction, then we speak about the developed finite element model. After I will speak about the experimental and sensitivity finite element analysis, and finally I will move to the conclusion. So in recent years, many creative solutions for pipeline design due to their importance in transporting energy and water have been developed. In fact, the behavior of the pipe receives a great attention of researchers due to its wide application in engineering, where the crack problems of structure have been extensively studied by different researchers and engineers. As Lee and al., who developed a new method based on the committee network to define the location and size of the crack of steel cantilever notched pipe. Lee and al. Detected also the pipe's crack experimentally by adding virtual masses on the substructure combined with the sensitivity and frequencies. Moreover, Khatir and al. Carried out a numerical simulation based on genetic algorithm in order to identify the cracks damage where different value of natural frequencies have been determined. Other methods have been also used by the same authors as the extended isogeometric method in order to identify the effect of the damage. So the key of a good conception of the pipes and structural health monitoring is the identification of the crack location and depth. So in our study, numerical and experimental analysis have been done where the ANSYS software has been used to model the cracked and cracked pipe, and the obtained frequencies from the numerical analysis have been compared to those obtained from the experimental one. The effect of different parameters as the types of mesh, number of elements have been also studied. So now I speak about the numerical study where the characteristics of the pipe are resumed in this table. However, in order to quantify the effect of the crack depth on the behavior of the pipe, a finite element model of a pipe has been developed. And different depth of pipe single crack have been created in the middle of the pipe as shown in those figures. In the second part of our study, the vibration of the cracked and uncracked pipe has been analyzed experimentally where the MPSO analyzer has been used. The excitation have been generated by a hammer and response have been measured for each depth of crack, where the three modes shape have been determined and the obtained results have been resumed in this table. From this later, we can conclude that the obtained results from the finite element analysis are good compared with the experimental results, which allows us to prove the importance of the developed model. It can also observe that the crack's depth has a great influence on the response of the pipe. So when the crack's depth increase, the natural frequencies decrease, where these figures represent the three mode shapes for two types of cracks depth. Moreover, different specimens of pipes configuration have been analyzed where the obtained frequencies of 1D and 3D have been resumed in table 3. From this analysis, it can be concluded that the 3D configuration allows us to obtain accurate results. Furthermore, the sensitivity of the used mesh is also studied for 1D and 3D, and the obtained results have been resumed in table 4. From this later, it can be observed that when the number of elements increases for 1D, the value of frequencies converge. And when the pipe is divided on more than 50 elements, there isn't any change on the value of frequencies. And finally, the three types of pipes mesh have been also chosen in order to determine the different frequencies of the pipe by using 3D-defined element model, where the obtained results are summarized in table 5. From this later, we can conclude that the tetrahedron pipes mesh allows us to obtain better results than the others. So from this study, we can conclude that the efficiency of the developed model has been verified by making a comparison between numerical and experimental results. Many parameters have been also analyzed in this study, such as the types of mesh and the pipe's configuration. The depth of the crack has a strong influence on the response of the pipe, where the value of the frequency decrease with the increase of the crack's depth. And finally, we can say that chosen types of pipes configuration and meshing play a major role in the determination of the real response of the cracked and uncracked pipe. Thank you for your attention.
Okay, thank you, Miriam, for a nice presentation. So if someone has a question, you're welcome to ask.
Hello,
Yes.
I have a question.
Yeah, you're welcome.
Can you show the how about the stiffness of the spring when you simulation in the ANSYS? How can decide this, the stiffness when you simulation in the ANSYS of the spring, the hang the pie, the spring with hang the pie?
Yes, okay. Yes, Miriam, yes, can you reply? Did you understand the question first?
No, I didn't.
He asked about the spring loading pipe, the loaded pipe, the springs. Did you?
There isn't any springs because the pipes are free.
So she didn't consider the springs or the rigidity of the springs because the condition it's a free. So
that's why, yeah.
Okay.
Yeah.
So there isn't any.
But I think to improve more accurate results, she has to consider the rigidity of the loaded pipe.
Yeah, sure. We'll do it in the future.
Yeah. Okay. Okay, there is no more questions about
any question?
Presentation. If not, we can go to the next presentation. I think this is the last one. Cracking behavior of corroded beams repaired in flexure by steel fiber reinforced concrete. So Tan Trong Nyen. So is here or no? Yes, Kong. Where are you, Kong? Kong.
Yes, I'm here.
Yes, can you see the last one? Please.
Yes, the last one, I think the last one, then boy, I think the last one is will missing. This guy, he not be here.
I think
the last one in our presentation. Sorry for organizer.
Okay, so you're here. Okay, good. Okay, good. Okay, good. Okay, now you can share your presentation.
Hello, Jaime.
Yes, I'm still waiting.
Who will do the presentation?
Someone will do. I think he's still sharing his presentation, but I don't know.
If then no one, we can.
No, he's here. He's here. He just mentioned that we'll do.
Who?
The last one, Strong. Yes, Strong. Are you here?
Which paper?
The last one. The last one. Cracking.
Yeah, we went because this guy he busy, so he cannot attend conference.
Why? He just mentioned that presentation. Do you know him? Or?
No. Here we can stop because here he lets me know.
Ah, he lets me. Ah, okay. If he lets you know, okay, it's okay. So I would like to thank all the presenters for attending the first day of our conference. So tomorrow we'll start at I don't know, at 9.
Nice.
So, yes, 9 a.m. So there are 4 missing presentations. So 2 of them they asked to do presentation for tomorrow. So we will try tomorrow to schedule them. So I think everything is okay today. So, and then tomorrow for the after the last presentation, we will close our conference by me and Dr. Kong. Okay.
Yes,
so if you want to say something, Dr. Kong.
Yes, so we thank you our participant. Also thank you Professor Nguyễn Minh Hà, Dr. Semi, Professor Nguyễn Trọng Phước. We also finished the first day, and I think today there are many interesting presentations, and we hope tomorrow we will see more interesting presentation, and tomorrow we will meet again, and Professor Dương Hồng Thẩm will chair the section 3 application for structural health monitoring, and we will start 9 a.m. tomorrow.
Okay. Yeah, 9 a.m. tomorrow. Yeah.
Yes. See you tomorrow.
Okay. Bye.
Okay. Bye.
Yes.
See you tomorrow.
See
you tomorrow. Bye.
Thank you.
Bye. Thank you.
Thank
you very much.
Okay. Bye.
Take care.
Bye. Bye. See you.